So I want to go ahead and welcome all of you to the NSMCon 2020 EU. We should be starting in about 2 minutes. Just want to give folks a chance to show up. We're also live on the Network Service Mesh channel on YouTube. We are somewhat oversubscribed for our capacity unexpectedly. And so we have that as a second channel. I'd also encourage all of you to please click the participate button. You can come over to the Network Service Mesh channel on Slack. There's a Slack invite for CNCF if you don't have an account there. And you should be able to ask questions from speakers after their talks and also socialize with each other, which is always a very enjoyable experience. It's an attempt to recreate some of the being there hallway track sort of experience. So welcome to NSMCon EU 2020. I appreciate you all being here. This is our first time doing a virtual event. So far it's going extremely well. Our first talk up this morning is actually our keynote. It's from one of our event sponsors, Anthem. Here to talk about basically edge infrastructure, network service mesh, and I believe things related to zero trust networking. So we have Bobby Samuel, Staff VP of Engineering at Anthem Inc., and Frederick Kautz, Head of Edge Infrastructure at Dot.ai. Shall I turn it over to the two of you and stop sharing?
Yes, please.
All right. All the sharing should belong to you now.
Okay, quick check. Can everyone see the screen? Okay, I see heads bobbing. Cool. So welcome to Network Service Mesh. And so I'm Frederick Kautz, Head of Edge Infrastructure at Doc.ai, and we have Bobby.
Hey everyone, thanks for joining.
So Bobby is Staff VP of AI Engineering at Anthem.
So let me kick us off because when we talk about different technology and we talk about what is useful, what I want to do is I want to set the business context on the why. Why is Anthem doing this? Why are we spending time working in this space? So back in 2015, we had a large cyber breach or data breach. And those of us that were at Anthem, we know exactly where we were at the time it was announced. We knew when the pains that we went through. And as a result, we have beefed up our perimeter security, and we have a very talented network security and InfoSec team that works to protect our perimeter security as well as internal applications. And that comes with a cost, especially as we build scalable next-gen applications that reach out and touch different members and protect a growing amount of healthcare data. And then we've got as everyone may be aware, at least in the US market, there is just a continuous rising cost of healthcare. And that has driven the need for innovation. It's driven the need for, you've heard it many times in different ways, but faster, better, cheaper, right? Ways of deploying applications that are secure, that are scalable, and that are, available at a moment's notice. So as a result, we've been adopting zero trust network architecture and security model to drive cloud native app development. So groups that are participating, the open source projects are participating, and this is just a few of them, but the NSM, the OPA or the Open Policy Agent, Spiffy Spire are all helping us work together And there are different tool sets that come together to help us build this foundation. Next slide, please, Frederick. So as a result of that, there's a particular application that I'll talk about, or application set that we'll talk about, and it's called Health OS, at least within Anthem. And the idea of that is we're putting together an AI and security first set of applications that will come through multiple front end platforms. And what's powering this is our secure data set. There's a large amount of data we have within Anthem that we do the course of doing our business that we have available, and we use that to power these applications that are being built. We have a few in progress right now. Once we validate that, we will take Health OS and we'll make it available to the third-party development groups. So privileged groups that can come within our four walls and start to work with these data sets and unlock this supply and demand in the marketplace. We believe there's a ton of opportunity, a great deal of opportunity across the healthcare ecosystem. Next slide, please. So just to give you a quick idea of what this stack looks like, I'm going to start at the bottom and work our way up through this stack here very quickly. But we've got a large amount of data from different various data sources. Think of these as core operational transactional system data sources that are used to process everything from claims to lab values, et cetera, and as well as all of our operations type data or admin type data. We've got third-party data that's being piped in that we're using as a core to our business, as well as other solutions and services that we've been building, whether it's call center applications or various channels like that. And on top of that, we've put together a data ontology, if you will, and there's access APIs as well as MDM that we're following for master data management to make that available and to abstract everyone from that data layer that's down below what we live in. On top of that sit various channels or apps that get built and that are actually all in use today. So everything from a lifetime patient record or a longitudinal view of a patient record to AI-driven insights and population health or care gap awareness tools. And so we sit from there, from that point on, our SDK sits on top of that. And in that SDK, we've been developing apps that are various types of products that start to deploy useful bits of functionality out to the world, everything from chatbots to other types of channels that we can deliver. And those all sit on this Health OS stack and platform. So they are security first application. So security is not something we think of after the fact. It's core to what we do using SPIFFE, Spire, OPA, and NSM. We put those together. The code stack sits there, as well as a design system that we've put in place that help with the look and feel and the performance of all these different apps. So that's where we're starting. This is where we've begun, and NSM is core to our journey as we begin to look at this. And zero trust is we're a big believer in zero trust being one of the big answers to how we can scale next generation applications within the Health OS system. All right, next slide.
So let's start a little bit about how NSM fits into this picture. And so I'm one of the people who helped architect Health OS, just for some context. And what we're looking at is multiple systems communicating with each other. Many of them may not be in the same organization. And so there's a lot of complexity there. And what we're trying to do is we're trying to establish the system in such a way that we have three basic patterns. From the pattern of the application developer, which we're calling the user in this scenario, they have a workload, typically a pod in Kubernetes. They want to connect to something that is outside of their system. Could be something in a secure environment. Then they just want to be able to ask for a network service, and they receive it. From the operator's perspective, the operator wants to say, well, what does that really mean? I want it to go by policy through a firewall, intrusion detection, through VPN, and they can declaratively state the type of things that they want, and it gets composed into the system. From the vendor of the network service, what they want is they don't care about what comes before them or after them. They want to say, I'm a network service. I can speak in this specific way. I provide this type of a service with a certain payload, such as IP, and I don't care about what comes before or after. I just want to handle what I need to do based upon my configuration. So NSM, based upon where you're coming from, appears to have this type of property to you, and it abstracts in a way that you don't have to worry too much about what is the user doing, what is the operator doing, or vendor, depending on who you are. So one of the things that we're pushing towards is a zero trust environment. And when we say zero trust, typically you have to look at the past. What does this mean? So historically, most systems, you have a trusted network, and there'll be workloads on that trusted network. And suppose you want to connect to a workload that's outside of your trusted network, inside of another one. Then what you typically have to do is you have to join up these networks. You have to do things like subnet deconflicting and so on, and try to work out or perform network address translation and try to cook these things together. And your root of trust is primarily at the network level, and you put your access control list with your firewalls to determine who can talk to who. And your workloads may have some additional features, but it's not core to your infrastructure. It's something add-on that the applications do. When we say zero trust, what we specifically mean is that this is now this trust from workload to workload is now part of your infrastructure, and it gets attested and validated. And we still have networks. You could still have a perimeter that is your network, but it's no longer your central root of trust. Your central root of trust is the actual workload itself. It receives a cryptographic identity that says, I am who I am, and it's capable to use that identity to connect and make use of services. And if you notice, the tunnel is now connected from trusted workload to trusted workload. So we also have on the horizon 5G, and this is a little bit forward-looking in terms of where the industry is going as a person who's working on network service mesh. And so many companies are starting to look at, well, how do we gain access into such a system? And so a couple facts: 5G radios are being deployed rapidly. The current backend infrastructure for those radios is currently 4G, but the next generation telecom infrastructure is being designed today, which is going to be horizontally scalable. The reason it's going to be horizontally scalable is when you start to look at the density. And so people, they look at it and say, oh, I get all this fast bandwidth. Actually, the real exciting part about this stuff is around how many devices you can put in a given area. And so this is going to enable machine-to-machine work. This is one of the key things that is necessary to actually realize the vision of IoT. And what will happen is that there are edge data centers that are being designed, and there's some in early deployment where an edge data center you can think of as a data center that's very close to you. It may be within a mile or two from where you're at, that your devices are able to connect to. And so when we start to look at this in an environment where, like, what does this mean to organizations, and not just healthcare, but just across the system. So I came up with this particular example to show what a system may look like, and you can replace hospital with your corporate network or corporate environment. So what ends up happening is you may have a device that, instead of using Wi-Fi, uses 5G to connect to your local network and may connect to your local data center. That system may then connect through an edge data center to a cloud computing platform. And instead of hosting the firewall and intrusion detections directly themselves, they may end up tying directly into an edge data center that provides these type of things as a service. So you may have firewall as a service, intrusion detection as a service, all the way up leading into your cloud platform. So each of these particular things may be owned by a different entity. You may have the devices owned by a different entity, you have in this scenario the hospital network, the edge data center is another identity, firewall and intrusion detection as a service are different identities, and of course the cloud computing platform itself. And don't forget the connections between them are also managed by service providers who will have their own set of things that they want to interweave in. So identity becomes very important in this scenario, and the way that we avoid operational complexity in a scenario is we want to avoid having to deconflict subnets, avoid having to manage IPAM at a global level. You still need IPAM, but we don't want to say, okay, let's go deconflict everything. Let's go try to reduce this scope of what you're trying to reason about, reduce the workload privileges, and negotiate the total parameters. And NSM is able to play a key role in this particular space with that identity at the root. So if you're looking to help us on our journey, please join us in the NSM community. There's GitHub, Slack, there's weekly meetings. And if you're looking to help join us with implementing some of the things that you have seen on here, please contact either Bobby or myself, and we'll get you started. Thank you very much.
Excellent. Thank you, Bobby and Frederick. That was extremely good keynote. We're delighted to have had you guys here to speak. Thank you so much for all of your support. Let me go ahead and share the agenda, and we'll move forward to our next talk. So our next talk is Inside Network Service Mesh. And effectively, it's a talk about looking at the formal structures of what's really happening inside Network Service Mesh. Dominic Torno is the speaker. He has a real talent for making things simple and clear. Dominic, would you like to, I'll stop sharing, you can get going.
Absolutely, thank you very much for the introduction.
Are you able to turn your video on? I may have to tweak a knob, 1 second.
Unfortunately, I am not, since the room I am in is very dark.
That's completely fine.
But can you give me confirmation? Can you see the screen? Okay. Thank you. So welcome everybody to my presentation, Inside Service Mesh. I'm Dominic Torno. I'm a principal engineer at Cisco. And as Ed mentioned, I focus on systems thinking, on systems modeling, and specifically conceptual and formal modeling to aid the design and the documentation of complex software systems. Network Service Mesh is a cloud-native computing foundation sandbox project in the category cloud-native networking. And the obligatory "where is Waldo" question. Waldo is actually right in the center of the map. And in this talk, we will hunt for a clear and tangible mental model of network service mesh. What is a model? A mental model is a collection of facts. A collection so that every fact about the model is also a fact about the system. Mental models are the foundation of human reasoning. However, keep in mind that no model is or ever will be the system itself. Therefore, any model fails to represent the system fully. Today, we will develop 3 independent yet related models. First, a mental model of networking. Second, a mental model of services. And third, a mental model of network services in the context of network service mesh. What is a network? A distributed system is a set of interacting components. From here on out, since we are network-centric, we call these components endpoints. Endpoints interact by exchanging messages indirectly via a network. Without loss of generality, let's focus this discussion on two endpoints, E1 and E2. An endpoint is connected to the network via an outbox and an inbox for sending and receiving messages. Also, we keep track of the sequence of send events and receive events in an endpoint's history. If an endpoint wants to send a message, it will place that message in its outbox. And placing a message in its outbox is represented by a send event. The network picks up the message from the sending endpoint's outbox and determines the receiving endpoint's inbox. The network places a message in the receiving endpoint's inbox, and placing a message in its inbox is represented by a receive event. This can also be represented graphically as a time-space diagram. Each timeline represents an endpoint's history. Empty circles represent send events, and filled circles represent receive events. If necessary, we may also represent the network in this exchange. A request-response pair, from here on out called a transaction, is represented as two messages, the request and the response, and four events: the send request event, the receive request event, the send response event, and the receive response event. And again, if necessary, we may also represent the network in the message exchange. So from here on out, we will graphically represent an endpoint's inbox and outbox as one channel, only to keep diagrams concise. Okay, so far so good. We developed a model of a distributed system. Let us explore this model a bit further. In this model, we are able to take the viewpoint of the all-knowing observer. We can observe both the inbox and outbox of E1, as well as the inbox and outbox of E2 at the same time. E1 or E2 cannot. E1 can only observe its own inbox and its own outbox. It cannot reach beyond. So from the point of view of E1, the world is simple. Messages disappear from its outbox and messages appear in its inbox. The same for E2. E2 can only observe its own inbox and its own outbox. Again, it cannot reach beyond. So from the point of view of E2, the world is simple once again. Messages appear from its outbox and messages appear in its inbox. This is a fundamental realization. From the point of view of the all-knowing observer, E1 interacts with E2. For example, E1 may send a request to E2, and in return, E2 may send a response to E1. From the point of view of E1, it places a request in its outbox, and eventually a response appears in its inbox. Similarly, from the point of E2, a request appears in its inbox, and eventually it will place a response in its outbox. It is this very realization that lets us define the concept of a service. So what is a service? Not what is a network service. We're not there just yet. What is a service? Services are definitely everywhere. There is not a single blog post, talk, or presentation that does not mention services, or worse, microservices. However, rarely do the posts, talks, or presentations attempt to define services. In order to fully grasp the concept of a service, we need to discuss different points of view. The service-to-service point of view, the process-to-process point of view, the behavioral view, and the structural view. Here we will discuss these points of view using a simple example of a service consumer and a service provider. The service provider is a key value store. A service consumer may set the value for a key via a put command and get the value of a key via a get command. Here, keys are only integers and values are only strings. Now, from a behavioral point of view, a service is nothing but a contract. A contract on the sequence of events on a consumer's inbox and outbox. The central element is the contract of the key value store. If the client places a put command in its outbox, it will receive an OK, a confirmation in its inbox. And if the client places a get key command in its outbox, it will receive a value in its inbox. Now, from a service-to-service structural point of view, in our example, we have a service consumer and we want two key value stores, creatively named key value store 1 and key value store 2. Our requirements state that we must be able to store 1,000 keys in key value store 1 and 2,000 keys in key value store 2. It's an arbitrary restriction to make the example graspable. Okay, here the client sends a put 0a command to key value store 1 to set the key 0 to value a, and subsequently sets a put 1b command to key value store 1 to set the key 1 to value b. Then, when the client sends a get 0 command, it will receive a, and when the client sends a get 1 command, it will receive b. The same is true if the client sends this sequence of commands to key value store 2. The event sequences are absolutely identical. Now, how could we implement this? Here is an example. It's a simple Python Flask HTTP application that stores the key value pairs in memory. It exposes one HTTP route that accepts an integer key and responds to two HTTP methods, get and put. Get to get a value for a key, put to set a value for a key. But as we said, there is one gotcha. The process cannot store more than 1,000 keys. Remember, KVS 1 must be able to store up to 1,000 keys. KVS 2 must be able to store up to 2,000 keys. Therefore, KVS 1 is composed of only one process, whereas KVS 2 must be composed of at least two processes. For KVS 1, the sequence of events on a process level is identical to the sequence of events on a service level. However, for KVS 2, the world is different. Both process 1 and process 2 are able to store up to 1,000 keys. So in order to store 2,000 keys, we need to partition the key space. Here, we will store the keys 0, 2, 4, and all even keys in process 1, and 1, 3, 5, and all odd keys in process 2. Then, when the client sends a put 0a command to key VS1 to set the key 0 to value A, it has to be received at process 1. And subsequently, when the client sends a put 1b command to KVS1 to set the key 1 to value B, it has to receive at process 2. So while on a service level, the event sequence between client and KVS1 and the client and KVS2 are identical. On a process-to-process level, they are very different. However, they are indeed identical where it counts. The experience of the client, the sequence of events in its inbox and its outbox is identical. The contract is fulfilled. Furthermore, since the client is unable to look beyond its inbox and outbox, the client is indeed unable to observe the difference. The service-to-service and process-to-process structural point of view, they form a hierarchy. A service is indeed an emergent concept. Services are more than just the sum of their parts. Services are formed by a set of processes and their interactions. So intuitively, from a top-down point of view, the process-to-process level, on the process-to-process level, services exist at a set of constraints on the interaction, on the message exchange of processes. For example, for the key value store, that set of constraints determined that even keys were routed to process 1 and odd keys were routed to process 2. Now this gives us the foundation to determine what is a network service in the context of network service mesh. In the context of network service mesh, an endpoint, the provider, offers a network service. Another endpoint, the consumer, requests a network service. Then, in order to connect the consumer and the provider, network service mesh plumbs two network interfaces into the endpoints and spans a virtual wire, a point-to-point L2 or L3 connection between them. Like its physical counterpart, a virtual wire is a full duplex point-to-point connection. What you send is what you receive. That is, there is no frame or packet transformation on the wire itself. However, unlike its physical counterpart, a virtual wire may experience message loss and message reordering. An interesting aspect of a virtual wire is that of an addressing concept. Traditionally, messages carry a target address. The network determines the receiver based on that target address. If you are in a controlled environment, like for example in Kubernetes and in a Kubernetes network, you have as a developer a strong understanding of the address space. If you're in a more open environment, anything can happen. Now, the vWire gives us strong guarantees. The contract of a vWire guarantees that the receiver will always be the other end of the vWire. If network service mesh can span a vWire, it will adhere to this contract. So the network determines the receiver based on the network interface of the sender. For our key value store example, the client may request the network service key value store 1, and network service mesh will span a vWire between the client and the KVS1 process. The client may also request the network service KVS2. But KVS2 is composed of 2 processes to store key value pairs and 1 process to split between even and odd keys. Network service mesh spun a vWire between the even-odd splitter process and KVS2 processes 1 and 2. Additionally, network service mesh will span a vWire between the client and the even-odd splitter. We may rightfully say that network services are compositions. It's turtles all the way down. The vWire is a composition operator. We can have a look at the splitter. This is a simple even-odd splitter that once again exposes one HTTP route that takes an integer key. And it simply determines the modulo on this key to forward the HTTP request to another endpoint, either process 1 or process 2. And now we are able to explore the nature of network service mesh. A consumer requests a network service. For example, key value store 1. Then the network service mesh will plumb a network interface into the consumer. That is all the consumer can observe. The consumer may also request another network service, for example, key value store 2. Then the network service mesh will plumb another network interface into the consumer. And once again, this is all the consumer can observe. Now the consumer may send a put and get command to key value store 1 and receive responses via the first interface. And it may send put and get commands to key value store 2 and receive responses via the second interface. The fact that the consumer talks to a single process in case of key value store 1 and to multiple composed processes in case of key value store 2 is not only irrelevant, but in fact invisible to the consumer. Network service mesh gives us the primitives to compose complex services from simple components. that concludes the presentation. If we have some time, I'm more than happy to take questions.
So we do have a Q&A function in the Zoom webinar if folks would like to use that for questions. We also have in addition to the Q&A in the webinar, we also have the Network Service Mesh channel. Dominic, are you on the NSM channel on CNCF Slack so that folks can ask you questions after the talk?
I am.
Excellent. Do folks have any questions they would like to raise currently? So I think we have one in the chat from Charles Eckel. Is there any concept of virtual wires between services?
Yes, that depends a bit on your point of view. So on the process-to-process level point of view, virtual wires are spun between processes. But since processes make up services, you can argue that there is also the concept of a V-wire between a service and a service. Whereas you would say that the processes at the edge of service 1 and the process at the edge of service 2 are connected with this V-wire. However, interestingly, you can say yes, since the V-wire is also capable of composing services together once again. So as we saw in the keynote, so from simple processes you compose services, but these services can then further be composed by the processes at the edge. So yes, the V-wires can be viewed as being connections on a process-to-process level as well as a service-to-service level.
Excellent. So we have two more questions in the queue. And I apologize if I mispronounce your names. Nishith Tiwari asked in the chat, virtual wires, what are these, if you could elaborate?
The virtual wire is indeed just a contract. The virtual wire gives you the guarantee that if you put one message in at the one end, it will come out at the other end, just as a physical wire. So interestingly, virtual wires actually have the effect, as we already discussed, networking. In networks, you communicate indirectly via a network. Virtual wires have the interesting effect that their contract actually gives you a direct communication semantic. So network service mesh implements direct communication on an indirect message. But the point is, it is more of a contract, similar to, for example, how the Kubernetes networking model is a contract. The contract of the virtual wire states that everything that goes in one end comes out the other, and vice versa, however it is implemented.
Excellent. So we have one more question this time on the Q&A from Tom Kivlin. How possible / feasible is it to create virtual wires with traditional infrastructure, i.e. Virtual machines, bare metal based operating systems, or even underlying network infrastructure?
I would love to actually hand this question back to Ed, because I know that this is one of the reasons that makes network service mesh so powerful. It is absolutely possible, and I'm sure Ed has lots to say about that. I'm sorry if I just like throw the ball your direction, Ed.
No, that's completely fine. I mean, it's a fairly deep networking question. And probably one that's going to be really entertaining to discuss in the NSM channel as well. But essentially, in terms of feasibility to create traditional infrastructure, there's a lot of feasible ways to construct it, some of which are very familiar to you. So for example, every time we create a tunnel of some sort in our physical infrastructure, whether you're doing it with VXLAN, MPLS, whatever, we end up constructing things that look like virtual wires, or we can construct things that look like virtual wires and use them to connect things. But I think there's probably a great deal more depth in your question there, Tom. So I would suggest that we move that to the Slack channel at this time. Is that cool? Okay. All right. Thank you, Dominic.
Hey, thank you very much.
Excellent. So let me go ahead and share the agenda again. We will move right along. So next we have a break from the past, why CNFs must move beyond the NFV mentality, with speakers Jeffrey Salins and Watson. Are you guys ready to go? Hang on, let me actually enable the video for Watson really quickly. All right, so Watson, you should be able to turn on your video now. There we go. Excellent. You want me to go ahead and let you guys share?
There we go. Yeah, sure. I'll grab this here.
Cool.
All right, I think that looks good. All right, so good morning and welcome to Break from the Past, why CNFs must move beyond the NFV mentality. My name is W. Watson. I'm with Voc Co-op, and I'm joined by Jeffrey Salins, who's with Charter Communications. And I hope that you enjoy what we have provided for you today. So on our agenda, we're going to talk a bit about cloud native ideology, and we're going to have a little fun with some buzzword bingo. And then we're going to talk a bit about the SDN space. And then we're going to talk a bit about the service provider pain and different ways to address that pain using NSM in the development process. So it's going to be a lot of talk about regular software development processes there. And so cloud native ideology, what does ideology mean, right? So ideology can have many definitions, ranging from a pejorative term for that which is wrong to a fantasy that covers inconvenient truths, right? So the term cloud native has many ideological definitions, starting with no one knows what cloud native means, which falls under that which is wrong extreme, right? And then on the other extreme, we tend to treat cloud native as a panacea, which falls under the fantasy category, right? So you have a spectrum there. Okay, so to me, a clue to how to reason about cloud native ideas, and this kind of runs along the line with the talk that we just went through, which I found very interesting. A middle ground can be found in the paper Programming in the Large versus Programming in the Small by Frank de Riemer and Hans Kron, written back in 1975. A problem that's been plaguing programming for 45 plus years is figuring out how to reason about, define, and direct several programs, components, or modules as a system. When we look at cloud native principles as a whole, it's analogous to reasoning about programming in a large. But various domains of cloud native such as containerization, CI/CD, orchestration, observability, service meshes, networking, etc., can be associated with programming in the small. Some aspects of the higher level are found in the lower level and vice versa. So on this view, with respect to networking, the right question to ask might be, how do we take cloud native principles and apply them to the individual domain of networking? For cloud native in the large, networking often means service mesh networking, such as service discovery, health checking, routing for REST services, load balancing, authentication and authorization, and even the generation of observability metrics and tracing, right? So that's kind of like the service mesh idea of what a data plane is, and not for this crowd, but more for the traditional service mesh. And those are mostly layer 7 concerns that address the networking of components or modules as a system. For cloud native in the small, networking concerns go down to layer 2, with even implications that might go down to layer 1 for cloud native in the small. In the words of Ed, the packet is the payload. So how do we address this? Move this out the way here. Okay. All right. So, how is it that we address this this confrontation of the higher level and the lower level, and maybe some of the conflicts that happen with trying to define terms and such, right? The result of really any critique of an architectural offering should really be the trade-offs of that offering. Okay, so critiquing the promise of cloud native should be no different. We should force ourselves to define what we mean when we use cloud native terms. And we can do this by playing something like Buzzword Bingo during our talks, papers, and conferences to keep us from relying too heavily on buzzwords and extreme ideological positions. When hearing a description of cloud native networks, try asking yourself the following questions. Does this description sound like a high-level enterprise application concept, and does it address my networking challenges? Is it a traditional SDN networking concept with new names, essentially rebranded? And are the terms being used defined well enough? I think those are that's like the gauntlet I think that we need to lay down. And within this group, we kind of lay down that gauntlet pretty well. Within the larger like CNCF group and some of the other communities, Kubernetes communities, I think we need to lay down the gauntlet a little bit better than what we've been doing. And now I'm gonna hand off to Jeffrey.
Okay, can you guys hear me okay?
Yeah.
So yeah, NFV and SDN, like I'm going to talk a little bit about some of the challenges I've hit from working on both the vendor side and the provider side. Just kind of go over, what I think was lacking based on the ideology that Watson just laid out. And then, this kind of leads into why we started to chase something like network service mesh. So, I mean, first of all, in my opinion, SDN is the champion of all buzzwords. I guarantee you, let me see how many people. We have 79 participants right now. I bet if I asked all of you what SDN was, I'd get 79 different answers. Is it an API abstraction that I write my own custom Python on top of? Is it, some SDN controller that pushes open flow route injections and stuff and messes with somebody's route table? Is it just orchestration? You know, where does the policy versus configuration management fit? Like, it's just a completely overloaded term. And at the end of the day, I have to ask, you know, what problem were we solving? I think the answer people would give is that it was supposed to reduce complexity, but I feel like it did the opposite personally. We get like these central controllers that are supposed to do everything, and then we get into this endless loop of how many southbound adapters do I need to develop to actually talk to all these different vendors. And that's kind of like one of the key things too, is me as a provider, I consume technology from lots and lots of different telco vendors. Name an SDN controller where I can like go in and talk to 4 different vendors, switches, and program, you know, data centers, fabric path or something. Like, it's next to impossible. I can do it with their stuff, but I can't do it with someone else's stuff, right? Like, it's almost always a greenfield experience, and my brownfield is always forgotten. You know, sorry you spent all that money on those legacy switches, but you need to throw them out and buy our whole new system so that way you can do quote unquote SDN. Then you have virtualization, like all 50 shades of it. I mean, this one is even more challenging, and this is kind of why I think a lot of providers are looking at cloud native, but like, there's a lot of cool ideas that just didn't pan out. We basically just kept the exact same model we had with PNFs, and we added a whole bunch of complexity. I took one packet core line card, and I directly swapped it out for one x86 rack mount. I put a single VM on it, and for all intents and purposes, I built an appliance, which I have to ask, if I'm going to go with an appliance-based architecture, why wouldn't I just get a use case appliance that, you know, has a known set of parameters, a, you know, vendor-provided configuration guide, and is, you know, something that is easy to open up a TAC case on, like one TAC case, right? Like, I go and I talk to the packet core people, they know that CLI inside and out, they have direct access to the BU. Move it to the virtualization space, something breaks in. Do I talk to the packet core group? Do I talk to the Nano group? Do I talk to the virtualization group? Like, which layer of this stack am I actually troubleshooting right now? And then there's, you know, the things that most vendors get a little cross at me about when I bring up, and that's the fact that we all know that the vast majority of them took their PNF code, forklifted it, shoved it in the VM, and said we're virtualized. I feel like that lesson carried over. I do see a lot of, you know, quote unquote cloud native network functions that have been somewhat re-architected, not all of them, but you know, this resulted in a lot of interoperability errors, things like that. So basically, you know, that very bottom thing, the ROI, like, where was it, right? Like, I was promised that NFE was going to, you know, just drastically reduce all my OpEx. I think all it did was shift the OpEx. Like, there has been successful NFE deployments. I'm not saying there hasn't. There's people who have mastered this, but at the end of the day, you know, Watson talks about like the principles and the ideology of cloud native, and one of the biggest things is this declarative approach to how you consume services, right? Like, I put in the key terms at the beginning. We have this concept of Sarah. She is this, you know, angelic software developer who just puts out perfect containers everywhere, and we all consume it. And then we have these sneaky network people, as Ed likes to call them, and they're basically the bane of Sarah's existence. They literally exist only to impede everybody else's problems because we care about things like subnets, you know, route injections, things like that. And we want to know how stuff works. And I think that one of the main challenges with, you know, like NFE is the fact that at Sarah's level, everything was still completely imperative. If anybody's ever taken the time to fill out a network service descriptor or a VNF descriptor, it's an arduous process, and there is 8 million things that you need to account for to deploy, you know, this setting. So I mean, you didn't really abstract away any of the complexity you had when you had PNFs, when you were still going in and manually configuring everything. You just took all of that manual configuration and you shoved it into a text file. So, you know, this is one of the things that we consider, like, as we're looking at why would we move to a cloud native approach, and specifically look at, you know, how do I do cloud native networking, as Watson put it, versus forcing the cloud native space to conform to what I used to do in my previous iterations of, you know, virtual and physical networking. Anything you want to touch on the diagram, Watson?
Nope, that sounds good. We'll switch over to the to the next piece here. So I'm going to go a little off the cuff here. So I'm, a little bit about me. I'm really just a pure programmer. I've been programming since I was 12 years old for over 30 years. And one of the things that I'm drawn to is pain, like a user's pain, other developers' pain, so on and so forth. And I attended a conference, Open Source Summit, maybe 3 or 4 years ago. And there was someone from TELUS that gave a presentation. They were a service provider in Canada. And they were just talking about this pain. And then all they put on their presentation were all things that had to do with just really the development process. They weren't really talking a lot about the technology, other than that it didn't satisfy what they wanted. And then I keep hearing this in the different environment, the different conferences that I'm at, whenever I talk with some service provider, even Jeffrey, the pain that they talk about, it's different than a lot of what within the, let's say, the cloud native community, what the pain that they're trying to address, right? So from my perspective, what I've seen for the past 2 or 3 years, as far as the pain that I've seen, service providers have the desire for speedy deployments and changes the code with minimal toil, right? So they want to apply security patches without having to upgrade everything in lockstep, for instance, right? We don't like development cycles or rollout cycles that are 6 months, or it's wild to me, but someone laughed at that when I was saying 2 or 3 months as far as a rollout. They're saying try 1 year. And being a developer, that just sounds extremely wild to me. That's going back to the 90s or early 2000s, right? So like I was saying, service providers, of course, they want a resilient infrastructure. Of course, networking needs to stay up. The network needs to stay up all the time. And then what's funny is that what many service providers, what they want or what they think they want is from cloud native is Kubernetes, right? So Kubernetes has the benefits that come with managing the lifecycle for your applications. Running Kubernetes seems to legitimize the containerization process that you may have previously done on your workloads. But there are problems with just adopting Kubernetes without changing your development process. And that's what I'm going to be talking a lot about. This premature adoption really gets the cart before the horse. The many desires of the service providers are solved higher up on the CNCF's cloud native trail map, which I'm showing here. And what you actually need, and then I'll go over here. What service providers actually need are the properties of Agile, the properties of speed, of deployments, and the ability to change code with minimal toil. This is supported by a strong continuous delivery process, which is often skipped on the trail to a cloud native, right? With continuous delivery, you have a process, a pipeline, right? That applies a series of tests at different stages. The first stage creates an artifact from the source code. The second stage tests the integration of that artifact with other artifacts, configuration, and resources in a test environment, right? And then the third stage and beyond can be manual tests, deployment into production or other environments. And I bring this out and talk about this because I see a lot of confusion about how you would bring this type of thing into fruition within a service provider's environment. You know, sometimes the later stages include tests of how well stacks of infrastructure work together, and right, so you could have a group of servers, switches, databases, in other words, and any grouping of elements that must be modified all at once, right? So that's a stack, and that's also handled within the continuous delivery, right? So really, the reason why you need continuous delivery is to pull the paint forward, right? And that's really the idea. The more you practice something, the easier it becomes. For service providers, this means preferring software and hardware options that lend themselves to the continuous delivery process. Okay? This means promoting, contributing to, and using open source, open hardware, bare metal switches, and commodity solutions that allow for completely automated deployments that separate, and this is important, separate artifacts from configuration and environments. If you use proprietary software and hardware, it can be harder to automate deployments. So the service providers need to demand the ability to make completely automated deploys with separate artifacts, configuration, environments from the vendors in order to get the benefits of an agile process. And that's what I think, really what I think when I hear the pain of service providers, that's what I think they need to address and how they need to address it.
Okay, so I know some of you are rolling your eyes right now, and it's like, obviously Watson, obviously Jeffrey, we're supposed to do CI/CD, but what does that actually mean? Especially when we start getting into the CNF space. Once again, thinking about some of the past pain from the SDN and NFV space is, how do I actually integrate my stack into the pipeline as a provider? I think one of the challenges for a telco or cable provider that's different than some of the more enterprise-centric companies is the sheer amount of end environments that we have and the sheer amount of operations groups, engineering groups, et cetera, that are all supposed to work in concert with each other. And so immutable infrastructure, this is one of the key tenets of a cloud native deployment. But what does that really mean? Especially in the network space, I think that a lot of people, when they hear immutable infrastructure, Buzzword Bingo kicks in. People start to roll their eyes. I can't have an immutable network. The big second bulleted thing there. Are you telling me I can't add a VLAN to an interface? This is always the first counterpoint I get when I say we should have immutable infrastructure. Is if you're telling me I can't modify my network device, then what good is the network device? If I have to completely nuke my data plane inside of my CNF because you're telling me I need to redeploy it every time I want to make a configuration change, it's worthless. And that's not what we're saying. What we're saying is we have to change how we approach the network. So, you always hear about all these Python for network, classes, this and that. Every network person is going to become a software person. When in reality, A, that hasn't happened. B, we still need people who know BGP way better than myself. People who are pushing the boundaries of segment routing and really getting into the nuts and bolts of what the actual network is trying to give us. But how we provision and consume the network, if we're going to quote unquote do it cloud native, then we have to do it the way that software people attack these problems. Why? Because cloud native approaches are about a shift in paradigm on the software side, right? So if we're going to apply cloud native principles, that means we're going to apply software principles to how we approach our network. And a big thing is if you're modifying any part of your stack in place, then you're not immutable. It's just, if you go and look at what immutable actually means, this is kind of Watson and I's line in the sand. If you're going in and you're touching a CLI, if you're going into a GUI, once again, this is any part of your stack, whether you're going into Horizon and OpenStack, if you're going into a device CLI, if you're using a vendor proprietary SDN solution and you're modifying things there directly in place, you're breaking the process. So where are we going? One more slide down for me, Watson. There we go. And so how do you actually get to a point where you do have an immutable stack? As you layer artifacts on top of each other, especially in a service provider when you're handing off from one group to the next, this whole concept of infrastructure as code, it also has to move beyond just a buzzword that we use to kind of like abstract everything and be like, oh yeah, you know, I have infrastructure as code, I wrote some Terraform, I have an Ansible playbook, I have a chef cookbook, you know, etc. Like, it has to be a complete paradigm shift, especially in a provider. You need to have every single part of your stack defined in code, a template, or an artifact that you can check in version control. So, you know, that means if you were writing like the Kubernetes deployment management system, all of that is defined in whichever templating, code, structure, et cetera, that you use, whether it's a bunch of Python that wraps kubeadm up and then allows people to deploy Kubernetes, whether you're doing it through something like Rancher or OpenShift, anything that you're using to do that provisioning, it gets checked in. Conversely, CNFs, network services through NSM, et cetera, everything is defined and checked in. And so what that means is if I need to change something, I always go back to the source, I make the modifications there, I check it back in, and then I let the pipeline do its work. If at any time I'm trying to, you know, trump or overcome the pipeline, I'm starting to break several of the tenets within the cloud native philosophy, and I'm therefore starting to reintroduce pain doing things the legacy way. And so, I mean, if you treat everything as code, you know, quote unquote, and I always think that that's also kind of like a misnomer because, you know, most of the time it's just templates and data models that you're pushing in and checking in to get. But this applies to configuration too. And this addresses that second point of, you know, do I have to nuke my CNF every time I want to change the configuration on it? And the answer is no, right? But what you should be doing is treating the configuration itself as an artifact, right? Figure out your favorite way of, you know, orchestrating something, regardless of what your poison of choice is for tooling. But then all of that gets captured, codified, and checked into source control. So if I have the makeup of, you know, a containerized router, it's got X, Y, and Z routes, it's got these policies configured for AAA, it's got, you know, X, Y, and Z RBAC stuff configured, etc. That entire thing is templated and it is then checked in. And some of this is going to be imperative, but as we go to the next slide, we're going to start looking at like the spectrum of declarative versus imperative type things. And let me real quick minimize everybody's faces here so I can see the whole slide. But first I'll let Watson kind of describe the spectrum, and then I'm going to talk about kind of how NSM in my mind fits into this and how it enables me, the sneaky network person, how it enables Sarah, you know, the person who's a lot better than I am, and then how we actually start to work with CNF vendors to kind of make some of this magic happen.
Sure. Can you hear me, Jeffrey?
Yeah.
Okay, cool. Right. Had a little technical malfunction in the background for me. So the declarative APIs, they allow us to say what, not how. This is what we say, what the state of the system will be, right? So we want to say this, what the state of the system will be and not how to get there. The declarative spectrum puts things like the local mechanisms like MIF and affinity decisions to the right of the spectrum with the CNF developers and the operators. The more to the left of the spectrum that you move, the higher the level of abstraction and the more declarative the API, right? And so I'll give it to you, Jeffrey.
Yeah, okay. So why I started watching and keeping up with network service mesh is because of how it, in my opinion, really does a good job of encompassing this entire spectrum. It has a little bit of something from everybody, for everybody. And I feel fortunate to follow the previous presentation, the explanation of systems, network services, services in general, et cetera. But you know, we focus on Sarah a lot in the CNCF space. I'll be honest, most of the time when people see what company I work for, they're like, well, why aren't you hanging out with the LFN crowd? Like, you know, you're tainted. You're just going to try to screw everything up and start whining about subnets here in a second. But in reality, you know, someone has to think about the imperative tasks. Like, these servers don't configure themselves. And, you know, the switches, the fabric, et cetera, like someone at some point wrote the imperative automation to create these upper level abstractions. And I would argue that Sarah does things imperatively. She does things imperatively in her applications. As she's building, you know, a portal, you know, for someone to consume, she's putting that entire backend together. She's imperatively saying how she's going to push and retrieve information from the database that's keeping track of all of her customers. But the question is what does she care about? She cares about her application. She does not care about, you know, the network. And that's why people like Ed have decided that, you know, we're going to rescue Sarah from people like me, the person who wants to like overanalyze everything on the network side. And Sarah does this by consuming network services. Once again, the previous presentation did a fantastic job of kind of showing what that is. And she can request it by name, right? If you look at Watson's definition of declarative, Sarah describes what she wants from the network, not how she wants to get it. And this is possible because NSM also provides the concept of building your own network services. You can go in and you can write these definitions. You can decide your order of preference for local mechanisms and remote mechanisms. If I'm a CNF vendor, I can get very imperative with NSM, so that way, you know, the operator there in the middle, who kind of has to wear both hats, can consume their CNF in a manner that is declarative. I can just say, I want X. I can then additionally write my own network services around something like what Frederick was showing. I can now put my own layer of abstraction on there, and every abstraction leaks, that's a fact. But there's the ability to figure out how I am going to, you know, expose APIs to each layer further up the stack. So if I have a CNF that is, you know, truly cloud native, it's composed of microservices, it's immutable once that artifact is shipped, et cetera, I can write a, you know, granular network service that says this is how all the components of my CNF fit together. Conversely, I consume that CNF as a complete package, right? There's going to be an API that's exposed. There's going to be interfaces that I can consume. I can set up virtual wires to and fro, et cetera. I put my network service on top of that, where I'm going to be imperative on how I want my network to run, but I don't necessarily want to have to be imperative on how I set up the CNF. And then conversely, you have Sarah at the uppermost, you know, furthest left abstraction, where she is now able to just say, I want this network service, which is, as you walk your way down the stack, comprised of what the overarching network service looks like, the macro level one at me as the service provider, which is stitching multiple CNFs together potentially. And then theoretically, this could be multiple vendor CNFs of different companies. I can then take their immutable artifacts and directly consume them. And so, you know, this, in my opinion, is a lot different than the way that NFV worked. NFV worked where typically it's like you have to deploy a VIM per vendor, because you get into all these weird KPI and SLA arguments. But at the end of the day, I would argue once again, if I have to deploy a unique OpenStack or vSphere environment for every single CNF I want to deploy, well, why am I doing it? Like, I might as well just get the PNFs. And so, you know, network service mesh, in my opinion, it creates bridges between Sarah and the SMPs. It gives me the ability to define the network how I need, and I hand, you know, an FTD in to Sarah that she can just use to request the services she wants, and she can focus on only worrying about the imperativeness in her application. Conditionally too, there's lots and lots of operation groups in the telco. We can now come together, check in a service into source control. We can put the necessary gates in place so everybody gets to, you know, feel like they were included and, you know, like sign off on it. But then after that, I can go across barriers. I can go across service providers potentially, like, you know, hopefully someday we write network services that define like how I do peering between, you know, myself and one of my peers / competitors, without having to worry about like, you know, do we each do, you know, X, Y, and Z configuration slightly different, like, because we're worried about the declarative approach versus the imperative approach. So let's go ahead and jump to the next slide and kind of talk about some challenges here.
Okay. Yeah, so Ed, jump in, give us the 5-minute warning. I'm losing track of time here. So
that's okay. You guys can keep going. I mean, we do have a break coming up after you, but we were sort of clear with folks. We probably were.
Great. All right. So, there are many challenges when applying cloud native principles to networking. One of the many challenges is identifying the requirements from the diverse service provider community. One type of requirement for larger service providers is the ability to procure solutions from multiple vendors. This means that vendors cannot sell solutions that do not play nice with vendor solutions, right? With service provider solutions. So a example of failure, let's say, of implementations in the past would be something like SNMP. I won't say complete failure, but as far as compatibility with the different solutions between vendors, right? So, and then some success stories would be ACDP and say, obviously IPv4, right? And so for me, the development process should be integrated in order to address some of that integration problem. Should be integrated with the procurement process to help facilitate multiple organizations, working with Conway's law and not against it. For larger service providers, this should include automated performance, security, and compliance testing stages in the continuous delivery process. I'll hand off to you, Jeffrey.
Yeah, so yeah, just kind of following up on what Watson says, the first one is big for us. And, full disclosure, I know that service providers, we ask for ridiculous things sometimes. And a lot of times vendors feel like they're herding cats. And I will make that admission, like we sometimes engineer ourselves into corners that are hard to get out of, and you have to rescue us. But conversely, so Watson put SNMP is a good example, but like, let's look at NetConf and Yang, which, is heavy in the, SDN space. Same thing with the Etsy Nano model, right? Like Souls 1 through 5 really didn't get a lot of love until the last couple of years. So like, I couldn't run vendor X NFVO with vendor Y's VNFM. It just was impossible. Like even just the whole indirect versus direct model of, where does the network, creation platform live? Does it live in the NFVO? Does it live in the VNFM? Go to Juniper, Cisco, Nokia, et cetera. Like they don't describe and model in Yang, BGP, OSPF the same way. So like we need to kind of figure out like, how, if we're going to do this in a cloud native way, we overcome those things. And then, Watson touched on Conway's law. I see network service mesh as a means of helping me overcome this. If I'm writing my own system based on how my organizational structure is set up, and I have a bunch of other groups within my company that are doing the same, how do we link our services together? And I feel like the way that network services were described is a good way to do that, right? I can work with my entity, build what I need to build, and then I can potentially work with another group where we describe a service that connects the two of them. Performance, this is like the Achilles heel of any time we're trying to move out of PNFs into VNFs or CNFs, right? Like if I don't get as much speed as I had in the PNF, then, I haven't like hit this nirvana of, virtualization or containerization, et cetera. But really what the question needs to be is, Watson said at the very beginning, you have to like weigh the pros and cons. What am I getting out of this transformation? Like, and is it worth it? How cloud native do I get with, still maintaining a comparable amount of performance from my infrastructure, right? Like if I can only get 10 packets per second out of 100 gig NIC, then things have gone horribly, horribly wrong. And maybe I shouldn't be doing what I'm doing, right? Conversely though, if I take, a very small hit in performance, but I do get things like elasticity, with, an elasticity in the sense that like I have true microservices and those individual services are elastic and I can scale them horizontally shrink them, basically use my resources on how they need to be used. Last big thing though is scale. And this is one I don't think we as a community have really figured out yet. I don't necessarily think that network service mesh magically makes this go away. But how many clusters do I run? If I go with the legacy model of, one K8s cluster per CNF, because you get into these weird issues on resource reservation, security concerns, et cetera. And instead of trying to address those, we just say, vendor, A gets, stack A, vendor B gets stack B, et cetera. But I mean, what's my master to worker ratio, right? If I'm hosting almost as many master and etcd nodes as I am worker nodes, something's gone awry. Like, how much compute am I going to consume? What does this look like at the edge? Am I going to host lots and lots and lots of individual Kubernetes clusters at the edge and burn up all those resources? Let's say I'm doing it in bare metal and I'm not, virtualizing these control plane nodes. Like, all of a sudden, the cost model just completely falls on its face. So I think that this is one of the things that, as we look at, cloud native network functions, if you will, if we're going to say that Kubernetes is the answer, then we need to figure this piece out, or I think, we're going to have some buyer's remorse in the future. And then let's go ahead and wrap it up here.
All right. The one thing I'm going to do is push back a little bit when you said that the network providers service providers are a little too pushy. I've worked on medical devices, hemodialysis machines, and so on and so forth. And I'm going to say, if you believe that when your software or your service goes down, people die, then you're not being too pushy. So,
no, that's fair.
I think that people should, I develop through empathy, right? If my user or my end user feels pain, that's what I'm developing too. And when, someone, if there's a certain amount of danger that's involved, I think that is a good driver for people to address that. So push the pain forward and let people address it. So that's what I'm a big believer in that. So as far as in conclusion, CNFs to qualify as cloud native, the ideology behind what it means to in fact be cloud native must be taken into consideration. Simply repackaging network functions and containers and deploying them with Kubernetes will not be enough to give service providers what they want or need. And while NSM might not be the silver bullet, right, with which nothing is, it is at least approaching the problem with cloud native considerations at the forefront, as opposed to being relegated to a nice to have afterthought. And I think that's in conclusion. We have some resources here. We have cloud native principles, which are tailored to a lot of what the benefits of to a service provider. And then also we have, as far as testing and trying to evaluate your vendors and your individual projects within your pipeline, we have the CNF test bed link and CNF conformance link as well there for you. And I think that concludes, unless you have anything, Jeffrey.
No, I think that does it.
Okay, so we are running a little behind. I would encourage folks to hit up Jeffrey or Watson on the Pound NSM Slack channel on CNCF Slack. And we're going to go ahead now and take about a 15-minute or so break. I'll put up a slide indicating when to be back for the duration of that period, and hope to see you all back here in just a few minutes. Welcome back, folks. Start encouraging you back towards coming back from your break. We will be very shortly starting with a new talk. Let me go ahead and get that queued up over here. Can folks hear me?
Yes.
Fantastic.
Yes, Ed, can hear you good.
Excellent. Give me 1 second to share that.
Cool. Can you remind people, scroll up a little bit to show them where they can join the NSM Slack channel to ask questions as well?
Yep. If you could please just click on participate, that'll take you to the NSM Slack channel and CNCF Slack. You don't have if you're not there already, you can click invite, Slack invite to get that invite. And give me 1 second while I queue up our next speakers in terms of giving them magical permissions to use videos and things.
Yeah, we have active conversations there as well, so feel free to hop in and ask any questions. And also feel free to ask questions through the Q&A here as well. And if we don't get to them, we can always shift those questions into the NSM channel on Slack.
Mm-hmm.
And there was also a question about the slides. And so what we're doing is that we're going to be updating the webpage, this particular agenda, which is on networkservicemesh.io in the events section, NSMCon EU 2020. And we'll be putting the slides into the schedule as well as we receive them.
Excellent. So hopefully folks have had a chance to get back again and get going. Are the speakers for our next talk ready to go? Ah, you do appear ready to go. Excellent.
I am trying to share it. Is it?
I see your share. Does everyone else see your share?
I'm able to see it as well. I think you are good to go.
Okay, thank you. Let me share my video as well. Okay, so hope you can hear me well as well. So hello and welcome all to the presentation of offloading data plane from the network services for telco use cases. So who are we? Myself, Roshni Ratnam. I work as a lead architect at Ericsson. So today you will hear from some more colleagues. Tariq Hammam, he's working as a system manager at Ericsson. Anders Francian, technology specialist at Ericsson. And Yuan Lunglet, developer from Ericsson. So what is our approach to NSM? So we are driving different studies that have been broadly looking at different possibilities given by NSM, and also looking at different areas that where things could be developed to further serve some of the telco use cases, also different network connectivity scenarios with Kubernetes using NSM. And we are also doing different experiments to look a bit beyond what NSM provides today out of the box. Also, we are looking at how architecture could conceptually be extended to accommodate some functionality prerequisites and decide properties for using telco networks. One among such architecture improvement that we have looked at is offloading data plane from NSM network service. So with that introduction, we will walk you through background, why we have looked into this whole architecture update and the use case. And we'll also walk you through experimental setup and a demo, and also a broadening of use cases with the concept that we are presenting, and also key takeaway from the presentation. So with that, Tariq Hammam will start describing the background. Tariq?
Is Tariq having difficulty with his audio? Let me check and see if there's something I can do to make that better. He should be fine for both audio and video, but he probably has to unmute them both.
Can you hear me now?
Yes.
Oh, yes, good. Excellent. Thank you.
Good. So, shall I start video here also? Let's see if that works. So, can anyone see me now or no?
I'm just seeing a black screen.
Oh, well. Okay, it worked with Skype, but yeah, that's interesting. Yeah, so I think we'll have to make do then without it if I can't. Yeah, fault locating may take some time here. Should have tested this with Zoom. Okay, so I'll start here with giving some background, basically to our thinking and also the demos that we're going to show. And one can't assume that everybody here in the audience is familiar with typical telco clusters, so I'll try to just take the essentials here and give the big picture to start with. In telco networks, in the core network, which is a higher part of the network, it's very common that the nodes, for instance, call handling nodes, network databases, policy databases of various sorts, they use some clustering technique, okay, for basically getting the processing capacity that they need. And then they are typically connected to some gateway setup, and that gateway setup is, it constitutes basically the demarcation toward the external networks, and also takes care of the interworking with external network and ultimately with remote parties on the other side of the external network. And the remote parties, that can be other telco nodes, which is the most common case, but it can also be user instruments like mobile telephones or other forms of user instruments. So this is a very abstract picture, and maybe it's worth to note that the gateway setup and the cluster setup, it's very common that that's part of the same telco equipment. But yeah, in some cases it can also be, the gateway parts can be part of various customer premises setups. I think we can take next picture. So going from this very abstract level here and look a bit more concrete and with Kubernetes and cloud native and so on, and NSM in particular, what is it that we want to achieve? Okay. So if we have our core handling services running here on application level in the Kubernetes cluster, okay, we need, of course, to connect somehow to this gateway setup. And that we do over some front-end devices in the cluster, okay, which have physical connectivity, of course, to the gateway setup. The most typical configuration is basically to use VLANs here, okay, so it's and normal routers, L3 routers, IP routers, and VLANs. And then we connect to an external network through these gateway routers. And on the other side, we have telco nodes and or user instruments. So the connectivity between the cluster and the gateway setup, that is of course is highly interesting for us, how that is done and how that's done effectively. Okay, and the other thing, of course, that comes to mind is capacity. One want to be able to handle the packets that come in, the traffic generated from the network in an effective way. Some form of fast pass solutions is sought. So I think we're getting ready for the next picture. So a little here about NSM and why we found NSM particularly interesting, and that is that NSM is logically based on a cluster-centric concept with distributed NSM clients. And that alone is of course not enough, but the NSM also has a concept of service endpoint, whereby an application pod, by means of NSM, on the client side, is provided access to a secondary interface associated with a corresponding NSM endpoint. So we get basically a framework here where we can start to do interesting things, okay, and model interesting things, okay. So then we start looking basically at the two issues I mentioned before. Okay, how do we do with basically the front end interconnection with NSM, and how do we basically get capacity into all this? So it is here suggested that offloading the data plane from the network services could facilitate a desired practice of front end interconnection to the external networks via a gateway setup. For instance, using VLANs, okay, in the most simple case. Furthermore, the said offloading would allow for an use of acceleration techniques in the data plane for a faster packet processing in the communication with the remote parties in the external network. And what we're thinking here is basically things like smart NICs and things like that to create a fast pass for the packet handling. And what we say here, that therefore it is desirable if the NSM architecture in its development trajectory would conceptually accommodate means for a client-invoked setting up of an application scope separated control and data plane, which would permit a delegation of packet handling to separate data plane devices. Okay, and these devices, I mean, that could be switches or things done you can think of it as switches, devices that are not in the pod but controlled from a Kubernetes pod. And we're trying to show this in some figures here and also our experiments. So we can take next picture. So if we start with the figure here, okay, we show a figure where we have a Kubernetes cluster, and then we have two pods. The green one, which is an application pod, which would correspond here to an NSM client, okay? And the application running in this pod would like to speak to the remote parties in the external network. But to do this, we need some help here from an NSM endpoint, okay, and we call it here the front-end endpoint. And the front-end endpoint basically runs software which controls, okay, the data plane or devices in the data plane that takes care of forwarding and also interconnect to the VLANs, okay, cross connect or interconnect to the VLANs. And then we have a control plane, of course, so that the pods can communicate and run the protocols necessary for NSM and so on. But the idea is basically to control the devices in the data plane primarily, okay. But then to achieve a fast pass. But then, of course, in some cases, it may be necessary also to have an optional way of getting packets, also some packets at least up to the front end pod, okay. A slow pass, you could see. That is not always needed, but sometimes needed. But the idea is to switch through the packets to the application. so that is basically what we want to achieve here. And so separating the control plane and data plane, that we think is key for a fast pass processing. Plus, it can facilitate the front-end connectivity, as we're going to show in our demo. I think we are ready for the next part of the presentation, which is the experimental setup and the demos, and I'll hand over to my colleagues here who can explain that, how we've done that in more detail. And then we will come back to the general model later on. Okay.
Yeah, can you hear me?
Yes.
Yes, everyone, loud and clear.
Okay, great. Try to turn on the video. Is it okay? I can see myself at least.
Go ahead, Johan.
Yeah. Roshini, I think you can share the slides, actually. Can you take it back?
Yes, please go ahead.
Okay, so this illustrates the test environment where we've done our proof of concept. And it's a quite standardized cluster. I mean, there are 4 worker nodes, and then there's an external router and switch. The only thing that might be of notice is that there's an extra interface on each of the nodes. Yeah, I think we can continue. So we start the procedure by deploying a VLAN NSE, the endpoint. So far, it's a quite standard NSM procedure, and it's deployed on one of the nodes. Yeah, let's continue. So here we have 4 clients that each request a VLAN from the NSE. So even here, it's quite like normal, like standardized NSEs and NSEs. And we can continue. And yeah, so here at this point, VLANs are injected into each of the NSEs, and they are created NSM0 interfaces. The difference here is that there is no NSE 0 interface created at all on the NSE side. They're only created here on the NSEs. Yeah, let's continue. So after that is done, it's possible to reach the NSEs from the external router after manual configuration. Let's note that configuration of the router is not part of the automatic setup done by NSM at this point. So by then, each of the NSEs should be directly accessible outside of the Kubernetes cluster. So to demonstrate this, we have a demo. And now I can take over the screen sharing. Is it looking okay?
Yes.
Okay. So here we have the 4 worker nodes as described in the previous slides. And yeah, these are the external routers, and we just use one in this case. So if we look at what has been deployed here, we can see that there is one NSE here and the 4 NSEs. And if we log into or access the NSE, you can see that there is no NSM0 interface here. So it's nothing on this side. And if we instead check in one of the clients, here we have that NSM0 interface we mentioned. And if we then, now I prepared this, but if we do this manual setup on the router here, and then we should be able to access just for demonstration purposes. So that is possible to reach it. And for other ones as well. So basically this demo is, we just want to illustrate what we wanted to achieve with the separation aspects. And by that, I think we can go back to the main presentation.
Thank you, Yuan. So this is the example demo that Yuan presented now, where you see the network service will only include the controller part, and it's not involved in the traffic flow. And by that, we will move to the broadening of use cases and key takeaways. Tariq and Anders will summarize the use cases with this improvement and takeaways of this presentation. Tariq.
Yes, so I'll try to see if we can get the video working now. Okay. Cameras more good by other apps. Okay. Please try again. This is hopeless. Okay, we'll have to make do without it. So Roshni, maybe you could just bring back the previous picture you had before we start looking at the broader cases. So if we look here at the demo, that all fitted into this model that we had here. But in the demo, there was basically the arrow, the bright arrow was from the FE controller, the data plane. That was not existing in the demo, it was not needed. Okay, so that was one case where this was not needed. A case where you would have a need for that is basically if you would run a routing protocol in the front end endpoint, okay, OSPF or ISIS, BGP or something like that, to announce IP addresses and attract traffic from the external network. Then you would need a slow pass, basically, to bring up packets like link state information and other things to the routing protocol that would be running in the pod in the network in the front end NSMCon endpoint. So that is one case. So this is a small broadening of the concept, but the same model, the optionality you need to have here to have flexibility. So I think flexibility is a key word. Okay, Roshan, I think we can take the rest now. So, yeah, here in this picture, what we've added is basically now we've added some service chaining here. Okay, we have added an intermediary, another function here, an intermediary function, which could be a load balancer or a router of some sort. Okay, and an application pod would then act as an NSM client, and the intermediary function would be both an NSM endpoint and an NSM client at the same time. And then there are many different cases here because there are cases where one would like to get packets up to that intermediary function and inspect them and do things with them and pass them on to a forwarder on the other side. Okay, but there are also cases where you would like to have a fast pass and switch through. Okay, packets coming from the external network or the VLANs, and for that you would need to have some form of conduit between the forwarder and cross connect this. The important thing is that there are a lot of different configurations and possibilities. But the thing that is good to have is an architecture that allows for this flexibility and have the concept that one can build this. And we know that allowing for having different data planes in NSM, that's work that's ongoing. So I think things like this could be part of that development in the future. Yes, Anders?
I just want to add, if I would tie back to the presentation Dominic had about, what NSM is. I mean, it is a process with an outbox and an inbox. What we have done here is to remove the endpoint 2 and made that one external, because we cannot build the complete world in NSM. We need to adapt to what's already out there. I mean, we have a lot of customers things that is already deployed. So then what we would like to do is to have like the endpoint 2 being like external, and we don't care for that in the application. We only care for the inbox and outbox of our application. I mean, we send something, we get something back, exactly as you said from the beginning.
Very well said. Okay, so it's basically delegating. It's all about the delegating to other devices. Okay, and keep the control in a pod in a endpoint, NSM endpoint. That's a key reoccurring thing here.
So there's a little bit of Q&A. If you guys, do you guys want to take a look?
We have one more picture maybe to
Perfect.
Take briefly here and before Q&A, and then we'll move to the Q&A straight. To take it a bit further, what is quite common here is that you have you also want to keep separation, VPN separation in the cluster, okay, and interworking with externally with the different remote parties, because they may reside in the completely different separated VPNs. And likewise, you would have applications, pods running that should just speak and communicate with remote parties in one particular VPN. So we've colored them here, blue, red, and green, and that would correspond to the VPNs, which are also colored blue, green, and red. And so that's one aspect. The other aspect, when we talk about the intermediary devices, you would like to have some of these intermediary devices inside the cluster also, like load balancers, and if you have a load balancer, then basically the traffic from the external VPN, they would come into the front ends, and then they would be load balanced over a number of pods of the same color. Okay. Things like that. But exactly, there are a lot of combinations and a lot of. So the good thing is to have at least with respect to NSM, a model that allows for this kind of flexibility. And we think that key to this is basically the offloading of the data plane. If one can do that, then it leaves the possibility to build flexible architecture. And as Anders here pointed out, basically the delegation to delegate the low-level packet handling to other devices. Okay. Then things would be very complete and very powerful.
Did I say that, Tarek? What I actually wanted to say that we don't want to implement the complete network service within NSM. We want to have the ability to have functions outside of NSM.
Yeah. So the external devices would be outside of NSM, but they could be controlled from NSM. That's what we intend. At least my intention. Great. Thanks.
So we got one question and that's answered, but still maybe it will be interesting for others to know. The VLAN tagging is done by the data plane, VPP, that was the question. So for the demo, it's done in the kernel forwarder. Though for the demo purpose, we have to hard code, but so that's the That's in the kernel forwarder that we have used in the demo.
Yeah, maybe we could add that the demo is a bit of a hackish. We are looking forward for this new NSM architecture with multiple forwarders, because then we could have a specific breakout forwarder made already, I guess.
Yep. We have a bit of a talk on some of that here a little later in the day as well.
Sure.
Okay, so are there any more questions? Otherwise, we are done with the demo.
Cool. I would encourage folks to, if you have further questions or want to have further discussion, to engage on the #NSM Slack channel at CNCF Slack. There have been some really good discussions happening there. We had a couple other questions that popped up on the Q&A. Do you want to go ahead and read those out and answer them live, or would you like me to read them out? I'm fine either way.
Okay. How to handle overlap between Kubernetes networking CIDRs, primitives, and NSM external routing?
Do you guys mind if I just drop a quick mention of exclude prefixes there?
Go ahead.
So Adele had asked about how do we handle overlap between Kubernetes networking kitters, primitives, and the NSM external routing. One of the things in the mechanics of network service meshes is negotiating its L2, L3 connection is from the client side. An exclude prefixes ends up being added by a component in the system that contains the kitters for Kubernetes networking. And so the network service endpoint, whatever it is put on notice that it's not okay to overlap with this. If they try and return an IP address to be assigned to the interface that overlaps with this, we won't actually do that for them. If they try and ask us to route IPs to them that overlap with those excluded kitters, we won't program those routes for them. And so effectively, we won't allow the stomping of the Kubernetes networking. Like we take a very, very strong first do no harm principle, and we put a lot of thought into making sure that whatever it is the network service mesh is doing, the standard Kubernetes networking works. Did it answer your question, Adele? Cool. Feel free to drop on the #NSM. We can talk more about that. Cool. Do you want to walk through some of the other questions that you guys have?
Yeah, one more is there. So is it like the forwarder creates a VLAN tagged interface, then forwarder injects that interface as NSM0? Yes, on the same node as the client is sitting.
Yeah, if this is the first request on the first service request. If it's the second service request, it will be NSM1, of course. And it is done on the forwarder that is closer on the same node as the client is sitting, at least with this implementation.
Does that answer the question?
I mean, it can be NSM1 or 2.
Yeah.
Cool. All right. I think sort of gotten to the end of the existing questions. I would encourage folks to pop onto the #NSM to continue those conversations, and we will move on to our next talk. So let me go ahead and share the agenda again. So next up, we have using DNS to smooth your NSM adoption with John Joyce and Tim Swanson. Let me go ahead and tweak things so that your videos will work, guys. Excellent. And I will stop sharing so you can start sharing.
Okay, great. Can you hear me okay?
Yeah. And other panelists who are just speaking, if you could make sure to mute yourselves.
Okay. And hope you're able to see that. Look good.
Yep, I can see it, John. Hey, it looks like you're sharing your second monitor, the one with the presenter view.
Oh, shoot. Let me do this. Okay. Is that better?
Yep.
Okay, so hello everybody. My name is John Joyce. Tim interjected there, sharing our video. We both work for Cisco Systems in our cloud business unit, working on, we've been working with NSM for a few years now, and we're trying some different things with it. And we want to show, we have a couple talks here, they'll have some overlap. On this particular one, we're going to show a little bit how we use DNS to help your NSM adoption and how that fits in well with some of the Kubernetes network, the embedded Kubernetes networking. So this is what we plan to show. We plan to show why you need to augment what Kubernetes naturally provides you, especially for use cases that are a little bit less service chaining and SDN based. We're going to talk about some of the different options that are available to provide those capabilities. We're going to show solutions that cover both the population side and the resolution side of the problem. We're going to show an API that we have started to create to try to simplify the implementation. This API has not been proposed more generally, but it is, we do have it open in case it's something that the community likes. And we're going to also showcase some additional open source projects outside of NSM that help with with portions of this problem. And we're going to show a demo, a little bit, a recorded demo. As it turns out, our lab crashed overnight, so we ended up, our recordings are going to be used instead of a live demo. So here's the landscape that we're dealing with a little bit. We have an application pod. We have, oops, I labeled it wrong. We have an application pod on one side with a network service client. We have an application pod on the other side. I don't show the NSEs in this picture. And we have in between there, we have NSM plumbed interfaces with some network, some arbitrary network. We have CNI interfaces with a Kubernetes-based network. And in some sense, these two networks could be overlapped in portions of the network or completely. We don't get into the details in this talk. We don't really care. What will happen normally with these application deployments is based on Kubernetes service objects and endpoint mappings. There's going to be some DNS system that's created and populated with mappings to some service here, service foo, to the K8's network IPs. Additionally, with NSM, in a lot of scenarios, we're going to plumb an interface, we're going to provide a network, and we actually want this pod to communicate with this pod via this network and these interfaces. We don't, I mean, sometimes we might, but in this particular example, we're showing that we want to use this network and these interfaces. So how do we make that happen? Well, we got to make sure the client resolves. When the client, this is probably not the best said here on the slide, but when the client resolves, we want to make sure that it gets these mappings. We don't want the client to resolve and get these mappings. Otherwise, it'll use the wrong paths and the wrong mappings. So that's the sort of general problem space that we're trying to deal with. So for this, here we're talking about, okay, what's in master, okay? And this is part of the solution. So we have code in master that's merged to help with the resolution side of this issue. We have a few details later on at a high level. There's a configuration available to direct the client resolution the way you want it to. The information is passed via the connection context it relies on some additional logic in the NSE to populate the context, and it utilizes a core DNS server that's running within the pod. That core DNS server in the pod is inserted by the admission webhook. It's the normal NSM configuration. You get it by default unless you do something special. And when we use this path, we don't require any customization of the DNS configuration. By that, I mean just the out-of-the-box KH DNS configuration will work. The details, I have a pointer there to the details. It's on master, so everybody can look at it. There's nothing special about that. And I point out here that there's also an optional fan out plugin documented there, which will handle cases where there's conflicts. That optional fan out is not the default that's in master. But nothing in master actually helps with the DNS of population. This is all with the DNS resolution side. So this is a little bit of a figure of how it works. We have the NSE that will have some logic to decide how the population gets, how the context gets populated. It'll populate the DNS context with some zone name and some server IP. The DNS monitor will deal with that context, and then it'll update the core file that the core DNS server within the application pod uses. And now resolution can happen via when core DNS, when the application pod does a request, core DNS will either direct the path this way or this way based on the zones. Okay. Tim, do you want to?
Sure, yeah. So as John described, we have a solution within NSM upstream that that will resolve or allow resolution of with a specific DNS server, and that DNS server choice and zone information can be specified by an NSE or some other mechanism. So that's the resolution side of the problem. What we wanted to do was in our NSE implementation, we wanted to be able to have application pods control or have some control over how they presented themselves in DNS. So what we did was we created a population strategy. So we made a NSE API that the NSE can indicate what entries to be at, or basically the information required to add entries into any DNS system. And the details behind that are kind of specific to how the application wants to present itself for the NSM context. So in our API, how the NSE actually gets the parameters to populate that API and invoke the service. We use a standard NSE method of passing parameters from the connection within the connection request from the client to the NSE, and the NSE uses some key value pairs that we shove in there to actually turn that into the information that identifies the workload to this service. So on the other side of that API, we've implemented a server that essentially turns the workload information into DNS entries, and it's essentially it's not really using Kubernetes to do the DNS resolution. We're using the actual config for a specific zone and our own DNS server that's private to that NSM network that we've created between our NSEs. So John, the next slide. So this is the visualization of what I just explained. So we call this the workload service mapping API, and it's defined in our NSE repos API. package. So what this is showing is we have multiple NSEs in separate clusters, and we're really separating the view of cluster from DNS. So this is a sort of like a private DNS for a multi-cluster scenario with applications that are connected by network services. So in this picture, what we're showing on is where the pods with the hexagon are clients, and they are using the network service request to pass parameters to the NSE to and those parameters are identifying the workload that is running as in that client. So in cluster 1, you can see that the foo1 and foo2 pods are clients that are both implementing the service foo, and the NSE in processing the client connection request is going to associate those two workloads to the same service foo, and then fill in the endpoint information. So if you're familiar with the Kubernetes API, this is very similar in that concept of service and endpoint, or any load balancer config. This would be very similar to that idea. So, but we're just expressing service foo is implemented by these endpoints in these workloads. And there's additional information in this API, but this is the gist. And the NSEs will then post those using a gRPC service, post that to a service mapping server, and the service mapping server will is not specific to DNS, but so it's just containing these mappings of service identifier to endpoints, and it's going to turn. We have an external DNS client that turns that data into entries into external DNS providers. And external DNS is pretty cool. It's a project that basically puts a standard front end on DNS, and has a provider interface internally that hooks up with Route 53, Cloud DNS, Azure's DNS, and Core DNS. So it's very easy to create a standard sort of deployment of this, and then just have a environment specific provider config in external DNS that will populate your private DNS zone. So the next slide is so this picture, this additional call out is showing how the network service URL is able to, we're populating key value pairs there for our workload mapping service. So this is where the client would be able to present itself as, this is totally disjoint from Kubernetes. This is so that the client can present itself as a workload that of a service that it wants to let other members of this network service that it's a part of be populated with like DNS. So it's I guess the point is that we're allowing the clients to control essentially what workload they are and what service they're providing, totally separate from Kubernetes. So this is very specific to an NSM, other connected NSM workloads that would be able to access this exact instance over the workload over the NSM network service. So this is a bit about our some of the details of how this API looks, the current definition of it. So this is in our, like John was saying, this is a public repo for our NSE work. We pulled it out of the examples repo because we wanted to have a bit more control and CI. And so this we have a API package under there, and this is the service registry portion of that, and it has very few primitives. It's got a register workload service, a Git services streaming RPC, and remove workload service. So the workload details are broken out as I show on the right. This is just an object model service. At the highest level, there's a service workload object, and that's the place where the service identity is actually defined. And then it associates with one or more workload identities, and each workload has a corresponding set of IP addresses that one or more IP addresses that workload implements for that same service. So that's very similar to your normal Kubernetes model of services, but it's a bit simplified, and it's totally in our NSE's control. So why external DNS? I think external DNS was it's a project that seems to have a lot of support. There's a lot of provider implementations. We found it to be pretty well updated with, at least for the public cloud DNS providers that we were trying to use, mainly Route 53 and Cloud DNS in Google. And then core DNS works pretty well too as well. So we use that extensively in our private cloud setups. It's very, very, very easy to get going with. It didn't take us long to start using this. We were able to also populate. We were able to combine it with some additional population of a sort of like of the actual service endpoints for the RPC server, the gRPC server that I was showing in the previous picture. We were able to combine that with our custom entries that we were actually creating for the workloads and under the same zone. So that worked pretty well. And we used there's a CRD interface to convey mappings. So that actually provides a lot of ease of use for monitoring the state of what workload mappings have been created, and what their actual details are. So that's for troubleshooting. That's been a really strong feature for us. And just again, it supports tons of providers.
Okay, so now we're going to give a little bit of a demo. As I said here, we recorded the demo, so hope it all works out good and you're all able to see it. And I'm able to figure out the interface to share it, but let's go. The sequence a little bit is we're going to have an initial state where we have NSEs set up, NSM, a bunch of info like the service mapping server that we talked about. Then we're going to deploy a Hello World application, and we're going to show how that comes up and some of the details around it. We're going to show how external DNS comes into play, and then we're going to show the DNS records themselves, and then we're going to do some curls to prove it all works out. So let's see if I can get this rolling a little bit. Hopefully, it's not actually playing, is it?
Yeah, it's playing, John. You can see the counter increment, I think. Or maybe not.
Let me jump out here and see. No, it's not playing. So let me
it's ironic that the playing of the demo is not working.
Yeah.
The demo gods are striking very hard right now.
Okay, so yeah, that's kind of weird. Don't know exactly what's going on here. Okay, let me see if I can do it this way. Now it's playing. Let me skip ahead a little bit. Okay, so now we're going to go through it. I'm showing the infra components here. I'm showing external DNS, core DNS, and the naming is not the best here, but that's our service registry thing there. I hope everybody can see this. Now I'm showing within our cluster components, I'm showing that we have NSM installed and that we have a couple NSEs installed. I have 2 NSEs installed in the system, but because of our app deployment, only one of them will actually be in use. There's no application pods shown. And here's where we show the config map. So in this case, we're actually not using what's in master. We're actually updating the DNS config to point to a specific DNS server. This is our private server associated with the NSM network. So that config map is available to all the pods. And you can see we do an NS lookup here using that server, and there's currently no hello world pods. So now we're going to deploy the demo itself. And this takes a little bit. It has to do we're deploying the NSCs and they're connecting to the NSCs. The network services and all have to be plumbed. The B-wires has to be plumbed. All the NSM signaling is happening. So, and we're doing this in a kind of interdomain fashion, as we'll talk about later in another talk. So it takes a little bit. Now we can see that there's hello pods in the one cluster, and we'll see here there's hello pods in the other cluster. So now everything should be set up, and we're going to show how things start working. So we do an NS lookup from within a pod to that private server, and we can see we're getting actually DNS entries. And now we're going to do the same for the second service on the different cluster. You can see we're getting a different set of addresses. These are the NSM plumbed addresses. So we're going to curl from cluster 0 to cluster 1. And the key here is you'll see the instance name will be different, even though it's kind of, I cleared the screen, so it's hard to tell, but if you had memorized that instance in the half a second that I showed, you'd see that the instance here on the next curl will be different instances. So that shows it's all kind of working and the DNS resolution works. There's nothing special in these applications with respect to the DNS resolution. It's just a standard hello world stack. I think we borrowed this stack from Istio, to tell you the truth. And now we're going to show how the DNS, the CRD that we've created. So we've created a CRD for external DNS, and then external DNS picks that up and we'll populate it based on which provider we're using. In this case, the provider for this particular thing is core DNS. Here I'm showing what external DNS is doing. It's actually creating a key in our core DNS system. And that's the mapping to the NSM plumbed interface. And that's about it. So I'm glad I could get that working. So I have another demo here, and this demo, oops, sorry. This demo focuses on the population that's in master. This shows how we've can use master to handle the population path. If we, I'm sorry, not the population path, the resolution path. So we wanted to show how that works too. Oops, sorry, let me first give you a little context. This is kind of a repeat of the prior slide we had earlier, which shows how the system and master works. There's an NSE request. The NSE will populate the DNS context details based on whatever logic that is in the NSE. In our case, we'd wanted to use some of the labels and stuff that Tim showed you that we're doing for our service registry. But there's any logic you want could be used for that population. And then via the NSM manager connection processing, that context is available to the monitor pod and the core DNS config over in this the application pod. So here's the demo. Sorry, Ed, I know we're kind of roughly at time. There's only a few minutes here quickly on the demo that we'll just go through. This is a Jaeger trace that Tim captured to kind of show. It's a little hard to read. I apologize. I can't make it bigger without losing the video. So the video, it'll be available after the fact, but we're going to go through and show how we have the request and how we have the context, how we have information in the context with respect to how the resolution should happen.
So this is highlighting a lot of what's in the network service request message and how there's multiple stages. You can make a NSE that is a composite of multiple stages that add information or use information from the network service request connection context. So that's what this is. This is showing the connection context, which is information that is populated by each point in the processing of a network service request.
So now we're going to go into the actual pod and look at the core file that's available for the core DNS server within the application pod. And you can see here that it's added the 1096.0.10 is the standard core DNS, Kubernetes DNS server, and that additional context or zone we've added via this mechanism.
And just to reiterate, the core DNS, so this sidecar is the first point that's hit by DNS resolution for network service clients when it's installed by the admission controller. So you can see the default rules are for to hit the global DNS for anything that doesn't match a specific zone. And then the DNS context, what we just showed is when an NSE sets the DNS context, then entries get added into this core file in the sidecars config that can map to a specific a whole zone to a specific server. So that in this way, the DNS request wouldn't even hit the global Kubernetes DNS server.
Okay, and that's pretty much it. We're at Q&A. I don't know, Ed, if we went over time or not, and want to answer some questions here or just.
Yeah, we're running right up against time. So I know there were some really good questions about this that were popping up in the course of this. If you guys want to take that to the Time NSM channel, because the DNS stuff is really fascinating, and it's really interesting, the stuff you guys have done in terms of sort of dealing with the population side of it. So
Sure. We'll take those questions. So okay, thanks everybody for your time. Hope you enjoyed it.
Thanks, guys.
Excellent. Okay, so let me go ahead and reclaim the share. So our next talk up is on the NSM operator. So operators make pretty much everything in life easier, and we are really fortunate to have members of the community who are actively working on building and have built operators for network service mesh. Alexandre, Matt, are you guys able to get on your audio and video
Yeah, hello there.
Sure.
Can you hear me?
I see you.
Can you hear me?
That too. I hear
Okay,
you
cool.
too.
Okay, so let's go for it. Let me see if I can share my screen right now. Just a second. Yeah, I guess it's desktop 3.
So I think we have Matt Dorn as well. So we should probably do an audio check on both.
Hi,
Yes.
can you all hear me?
Yes,
Okay.
thanks.
Cool.
So good morning, good afternoon, good evening, whatever you are. Welcome to our NSM operator presentation. My name is Alexandre Menezes. You can call me Alex. I think it's a little bit easier. So I have today Matt Dorn, which is my colleague here. Do you want to say a few words, Matt?
Sure. Hi, everyone. My name is Matt Dorn. I'm a principal engineer at Red Hat and happy to be here to talk to you about the power of operators.
Yeah, so for today, we have a very simple agenda here that I'll try to keep it simple as much as I can. So I'll try to answer a first question, which is what is a Kubernetes operator? And then I'll try to give a quick introduction to the operator framework, which is passing through a lot of changes. And also I'll try to explore a little bit what it can add to the NSM infrastructure and application. Right. And at the end, if we have some time, I know that I am kind of in between you guys and the lunchtime. I don't know the time zones to everyone. If we have some time, I'll do a quick demo on OpenShift as well. So let's go for it. Right. So what are Kubernetes operators? So here I have a simple description on a definition for Kubernetes operators. And an operator is a method of packaging, deploying, and managing Kubernetes application by taking human operational knowledge and encoding it into software. So at this point, I know that I am diverging a little bit from the whole networking side of things, and I'm going to talk a little bit more about Kubernetes itself and how we can manage the workloads the NSM has using an external or let's say a microservice that can take care of its infrastructure. I know that NSM has a lot of complexity inside of it and takes care of a lot of things inside the networking domain, but I know as well that we have a lot of other things to be addressed that can be a very good use case for Kubernetes operators. So first and foremost, how can we define that in simple words? So it's a matter of packaging, okay, but what is actually an operator, right? We have three key things here. This is what I'm trying to use to keep it simple. So an operator is actually an API extension, right? In the sense that I can create a new resource inside of the Kubernetes API itself using CRDs that we already had the chance to hear about in some of our presentations in the beginning. But it's also a controller. Okay, so it's also a controller. And a controller, for those who don't know exactly what is a controller, is something that will be in an infinite loop, always talking to the Kubernetes API, watching for some specific resources, at least one resource, and will be reconciling those objects to their desired state, right? And in the end of the day, it is also a deployment because we are going to compile those two pieces of software together inside of a pod, right? So going a little bit further, let's recap what is a Kubernetes resource, right? So I like to just pinpoint like the four main fields that we have inside any Kubernetes object, right? What we have here is something like type metadata. Everyone, I'm pretty sure everyone saw this before. So we have the API group. We have the version for that particular API, that particular object. And we have also the kind for our resources, right? So the object metadata will have all those kinds of information that we need to manage the object itself when it is instantiated inside Kubernetes. We have name, namespace, annotations, labels, etc. Right? What is important to us here is the spec field. The spec field is the one that will define the desired state of some type of software, right? So the spec will be the one used by controllers to understand the state that we want on that object and reconcile that object to its desired state every time it's kind of going off the desired state, right? And this status field is something that we can use to put all sorts of informations that are important to us in terms of the health of that application. So we can just put like red, yellow, and green lights, but we can also sophisticate things, define phases, define every time of every type of timestamps and things like that. And here I just put a little phrase here that they are an endpoint in Kubernetes API, right? And what does the Kubernetes API give to us? So here is a list that I took straight from Kubernetes documentation. What we have in the Kubernetes API, like CRUD operations. So we can create, we can read, we can update, we can delete things in a very standardized way. So the watch operators via HTTP is the one that allows controllers to actually track resources, right? Discovery for some of the clients such as kubectl, for example, that will have the capability of editing objects and taking care of them. So, and immediately seeing that they are like live inside of the Kubernetes cluster. So then we have a bunch of others like JSON patch, we can patch, we can merge patch, we can use encryption using HTTPS, we can have built-in authentication, we can have built-in authorization. And here we share all of that RBAC infrastructure to authenticate and authorize as well specific users and service accounts and everything else. So it's coming with the API itself. We can use finalizers. Finalizers are the type of thing that will be used, for example, if you want to delete a secondary resource, and we are going to talk a little bit about them in a second. So finalizers will kind of do the cleanup, will kind of do take out of the mess or something that is like garbage collection, for example, and will only declare an object completely deleted if everything was done in a good way, right? So we see like admission webhooks to validate or even to mutate objects and a bunch of other characteristics, right? And all of that is shared among Kubernetes objects. So when I say that this is like an endpoint, so every single Kubernetes object will be behind the Kubernetes API, right? So just to give you a little bit of a sense on the Kubernetes API itself for those that are not familiar with that. So here's the canonical place for the Kubernetes API, right? So when I'm trying to develop something, develop an operator, I'll be dealing with a bunch of objects that are inside of this API, right? And here I have like a scrap copy of the same code where I have all the folders. And if I want to find an object here, I would go API like core v1, for example. I'll go to types. I think most of you must have seen this before. And then I can kind of, okay, I want to see the pod spec implementation, and I can see all the fields in here. So basically what I'm seeing here is actually the API itself, the grouping of those objects with the version, and inside the types.go, I can see the Golang types and a bunch of descriptions and indications of on how those objects work. But the question comes, if we can build our own CRD, we'll have all of that for us. We can develop our software on top of those CRDs, and they will share all those characteristics, will have the same kind of grouping and versioning and kind like the API gives us, and all those features together. So going a little bit further, what are the Kubernetes controllers, right? So I put like just 5 bullet points here. I think everyone is kind of a little bit used to them. So a controller is an infinite loop that keeps running and running and running. It will be tracking at least one Kubernetes object type, and it reconciles that object, the current state of that object based on the desired state that we have in the spec field. We just said that. And for reconciling it, it can interact with the Kubernetes API. This point is important because it can use the API itself to be like all the time reading the health and the state of those objects, but it can also control objects directly. And that is what is interesting. When you have something that is external to Kubernetes, you can go and actually develop something that is talking to a load balancer, a network appliance, or something like that. So we're going to talk a little bit about those kind of things. And I'm pretty sure that you guys that are working with NSM will probably have more ideas than I have at this point on how an operator could kind of enrich the NSM experience by bringing together other resources that would kind of complement the whole NSM infrastructure, right? So here is kind of a diagrammatic representation of what I'm trying to say. So for an operator, we'll have that controller that will be reconciling all those objects, that will be all watching all those objects. We have the CRD, which is the primary resource, and we have owned resource. So who is the MyCRD in that case here? Is the NSM infrastructure, the application itself that today we install using Helm, and Helm has its value. It can version things, it can like automate the installation, which is pretty cool, automate the updates for that, that installation. And NSM itself would be modeled like a CRD to be able to own certain resources. And so it could be deployments, daemon sets, stateful sets, and config maps as well. In that case, we have like the network service manager, the forwarder that we are using for that particular installation. We can use, for example, as a secondary resource and admission webhook, that in this case, with the new operator SDK that we'll talk a little bit, we have plenty of automations on that sense to put webhooks in place, right? So coming back to that question, how could we define Kubernetes operators in simple words? That's it. It's an extension to the API where we can see NSM as a native Kubernetes object. It will embed a controller that will be compiled or built into a deployment. That's the thing. I don't know if Matt wants to add something here or is okay there.
Yeah, it sounds good.
Okay, cool. So I'm going to pass through the second portion of this presentation. So a little introduction to the operator framework and talk a little bit about how it interacts with all of that we are talking at this point, right? So what is the operator framework, and then what are the key projects that we would like to highlight at this point? So it's an open source framework to make building operators easier, providing high-level APIs, abstractions, and code generation to quickly bootstrap new projects. What does it mean? So generation is the key word. We have some boilerplate code that is bootstrapped by some tools, and we are going to take a look right now at them. But just quickly, I would like to show you that at this point in time, and this is very, very recent, the operator framework now is part of the Cloud Native Computing Foundation. It's here under the incubating projects, right? So you can find it here, and you can look for a bunch of information here on its actual official website, right? So let's get back here and let's talk about the key projects for the operator framework. So first one is the operator SDK, which is actually a command line tool that will scaffold everything for us. So it will take care of the code itself that we have in terms of building that deployment that we were talking about, but it will do much more, right? Why? Because we have also metadata that we can build around our operator to publish the operator in the operator hub. So I'm going to show you that in a moment. It can also help us a lot with testing because it comes empowered with a lot of tools for testing those operators, right? The operator lifecycle manager, this is a part of it, of the operator framework, is kind of a little bit complicated, but I try to think it kind of like the infrastructure that helps us have each operator and then each application managed by those operators. It's the infrastructure that gets everything underneath it and presents as a software as a service platform, managing their updates, their upgrades, everything that is needed, and channeling versions and many other things, right? The community operators is another project that we also have. There is where we put our metadata for the operator in order for the operator to be published on the operator lifecycle manager. I know that I have a Red Hat badge here, but when I say OLM, OLM is completely open source, it's completely CNCF now, and OLM can be installed in any Kubernetes distribution. So you can have that, you can have the catalog of your applications inside Kubernetes, right? And just to give you a quick glimpse on the GitHub repos here, we have the operator SDK, so you can search for information here. We have also a second tool, and this is an important point that I would like to pinpoint here, which is the KubeBuilder. Why I'm talking about KubeBuilder? Operator SDK just got to version 1.0, and I'm going to show you really quick a little bit what happened when this change happened. So at this point, KubeBuilder is the main, let's say, the core engine of the operator SDK. So if any one of you is interested in developing an operator or in contributing with the NSM operator, this will be the new way to go. We have at this point, if we look into the network service mesh GitHub, we'll see the NSM operator over there. That has been kind of not touched in a while because it's being revamped to be compliant to KubeBuilder at this point, right? So, and here is something that I really, really recommend if you guys want to understand more, more in depth Kubernetes APIs, CRDs, watchers, listers, objects that will take care of all that kind of infrastructure, the API machinery, the controller runtime libraries inside Kubernetes. This is the KubeBuilder book that we use also as a resource to understand a little bit better what is happening under the hood, right? And finally, here in the operator SDK, we have the operator SDK website where you can find like building operators, Golang. We also can do operators, can build operators in Ansible and Helm as well. They have a few other caveats. They are not that powerful as Golang operators, but we can do. So for somebody that has already an Ansible script very well put together that can be leveraged to its maximum potential and be served into OLM catalog, this is a way to go. We can use Ansible or we can use Helm as well. So, and here you can take a look at the tutorials as well. So I do recommend if somebody is willing to develop an operator or to contribute to NSM operator to take a look into these two websites. So coming back a little bit, let me not get ahead of myself here. So what operator SDK brings to us, it is based on the controller runtime library. So it has a lot of already built-in code that Kubernetes uses and to run the operators, and KubeBuilder itself, which will be the one generating and scaffolding all the code. So it scaffolds a nice project directory layout, helps adding one or more resource APIs as CRDs, generates the base code, reconcile loop, the one we were talking about. So it will give you an empty reconciler for you to build your logic inside. So it helps a lot with that, building the managers that will run those controllers and everything else. It also facilitates watching resources by allowing us to list the owner's secondary resources, the one we talked about on that diagram. So helps development by running locally. So I can actually run my operator on my terminal, and it will be talking to a Kubernetes cluster anywhere on a VM or on the clouds, anything. So I can run locally to test and to develop and to improve. And will also help with all that metadata thing that I was talking about that will help build and publish the container, test accordingly to the community operators repo, and will generate all that metadata for you to manage inside the operator lifecycle manager. So the operator lifecycle manager is basically a tool that will provide the catalog that will give us that sense of, how should I put that, the sense of app store where you can click on your applications or just using the command line, you can list all the packages, all the operators that are available on a cluster, right? It will take care of all dependencies. So in case of the NSM, when we evolve a little bit, I know that you guys are using like Jagger tracing, for example, Aspire, for example. So I may have an operator for Jagger. I may have an operator for Aspire, and I can declare those operators as dependencies. And when I install NSM with a few check marks there, okay, I'm gonna call also the other APIs, right? Sorry, I just heard somebody trying to talk. I don't think so. Okay, so yeah, so it manages the dependencies as well, enables discovery, and a lot of other features that you gain from the operator life cycle manager. And in the end, we have the community operators, which is that repo that will allow us to put our operators into the hubs, both the OpenShift operator, embedded operator hub, and the operator hub.io, which is the one that you can pull all the community operators from there, right? Um, that's pretty much it about the projects. And I have kind of a workflow here that I try to make as simple as possible. There is a lot of things that could make this picture very busy, but in the end of the day, what I'm trying to say is we develop our operator, right? And we compile that operator into a container image. That image will be put to a registry, and at the same time, we build the metadata, and then we put that metadata into the community operators GitHub. From there, the OLM infrastructure, no matter what kind of Kubernetes distribution it is installed, it can take all operators from the community and present that platform with tons of applications, kind of in a software as a service feeling, because we'll have all of them listed, all the versions. You can you can make your decisions on what you want to install, what kind of version do you want to install, and things like that. And once you subscribe to an operator inside OLM, then it will pull the right images and run the right code to make it actually work on the platform. Okay, so yeah, that's pretty much it on that part. I have here the repo, the community operators, just to show you guys that I'm gonna pick up any one here, or even the NSM operator. I think I could take a look on the NSM operator metadata as well. Let me just find it here. This is not the one. Let me just see. I think I'm on the wrong folder here, so that may be the upstream one. I think that's, oh no, that's correct. That's the register one. That's correct. Just a quick second. Okay. I'm just, okay, here. Yes, this is the register that is holding the NSM metadata. I think, let me see. Yeah, this is, This is the one. So here I have all descriptions on the NSM operator in terms of metadata according to this picture. So I put it in the community operators hippo, and OLM can understand all of that, right? So going further, what it can add to the NSM application, right? So we have a maturity model that we use kind of to put a badge on the operators on the level they are. At this point, the NSM operator is kind of pre-alpha version. It's on the basic install method, but as a description here, an operator can go from basic install, just deploying your apps, to autopilot. So everything in between can be achieved. For instance, concerns like upgrades, downgrades, backups, restore, high availability, deep insights, and etc. And that's the classic picture that we use to explain that to people. So the basic install is basically putting it to run, right? And then seamless upgrades, it's a little bit more than just upgrading, but understanding the necessary steps to upgrade an application. And we can see that with Helm operators, we go up to the beginning of phase 2. When we go Ansible, we can go all the way in, and Golang also all the way in, being Golang the one that goes way further than that. And what could it represent in terms of seamless upgrades, like backup, failure recover, deep insights, like doing all sorts of analysis and grabbing data and kind of digesting that data into something that can bring value to the application, and also autopiloting, which could be basically understanding a baseline metric. And when the application comes out of that baseline, I already have some sort of action that the operator can take on behalf of the application, right? And this will be kind of a diagrammatic way of thinking things. So operator SDK is here. It's already inside the cluster. It's already talking to the Kubernetes API, right? And it can also deploy lots of other configurations outside the cluster. So it may be on-prem data centers. It can be like external block or object storage that are not, let's say, Kubernetes compliant, but you have a way to develop that logic. It can be cloud services in general, anything that you need to use for your cluster. It can be multiple external applications that are serving the cluster, but not inside the cluster. Then we can think all sorts of gateways and routers, network appliances, load balancers, firewalls, IDS, identity providers, and the list goes on. So here in this very simple picture, I'm pretty sure people that are on the NSM project for a long time now, they will have a lot of ideas, and I'll be very inclined to hear all of them and help whatever I can to put those features inside the NSM operator. So from that point on, I have a very quick demo just to show you guys that App Store kind of feeling that the operator gives us. And here I have an OpenShift cluster. I hope it works because this is a bleeding edge OpenShift. It is 4.6, not released yet, so it probably has a few bugs. And we have the operator hub with all the applications here. This is I can see the applications, right? I can see the operators that are managing a lot of stuff. I have all sorts of operators like Red Hat, certified, community, marketplace. It's out of scope to explain this here, but we have a lot of them, and NSM is also part of it, right? We will see the NSM operator inside OpenShift. At this point, we are kind of pushing to another layout the project, but we'll have it working pretty soon here. But we still can install the operator itself and the NSM application. So I have an NSM namespace here already created for me. And here, by the way, I have the network service mesh, and I could actually punt a few other APIs like network service or network service manager or network service endpoint. Those, by the way, are not actually working at this moment in time. And then when I install the NSM operator itself, I'll be able to, in a few seconds, just see the operator installing, changing. Okay, so now it is already installed. I know that it is running. So at this point, I can just grab the network service mesh infrastructure, and here I can create a new NSM installation, right? I could build from that metadata that I showed everything on top of this form, anything we want. At this point, what we have is just the name, some labels that I can put on. So what kind of forwarding plane, et cetera, if it is running insecure or secured, and the version. And we can also see the YAML format of this right here, right? So if I put it to install, it will create a new example NSM in this case. It will put it to run. I can actually see the installation here, look into the resources, and then it's deploying like an admission webhook certs, service, and also network service manager and a forwarder for the NSM application. Well, I think that's pretty much what I had to say today. Thank you everyone for your time. And are there any questions that I can address at this point?
Okay, I would encourage folks to reach out to Alexandre on #NSM, the #NSM Slack channel. He's a wealth of information about these things and has done a tremendous amount of work on both the NSM operator and also on smoothing things out with OpenShift, which is much appreciated. So thank you. So let me go ahead then. We have come to lunch. We're running about 15 minutes behind. So what I would suggest that we actually do is simply trim about 15 minutes off of lunch, since we're all here virtually, so we don't have to go walk to the local restaurant, hopefully. And I will go ahead and share up on the screen this slide that indicates that we are off at lunch and we'll be back at the top of the hour. And I hope to see you guys back at the top of the hour. We've got a lot more interesting content. Hello, we'll be getting going here in a little bit, about 2 minutes. All right, so we're going to go ahead and get going here at the top of the hour, which is a little less than a minute. So good time to wander back from lunch.
Hey, Ed, Tim got dropped or had to restart Zoom.
Hey, I'm back. Yeah, I'm back. Sorry.
I was just figuring that piece out, actually.
Okay.
Catalina decided to block Zoom from being allowed to share the screen, so I had to reset it.
Cool. All right, so welcome back, everyone. Hope folks are back from lunch at this point. We've got an excellent talk on NSM interdomain, functional walkthrough, and use cases. So I'll turn it over to Tim and John.
Okay, hi. My name is Tim Swanson. Can everybody see my slides, I guess, first question?
Yep.
Okay. So I'm Tim Swanson from Cisco Systems, and John Joyce is as well from Cisco, and we did a talk earlier on DNS. So this talk will be more on actually the NSM interdomain scenario. We'll do a functional walkthrough, some use cases, and we'll do a very quick demo. We have a lot of slides, so we're going to try and fly through this a little bit. So NSM interdomain. So if we talk about NSM interdomain, we have to really kind of understand, in the implications, we have to understand really the kind of the sort of primitives that NSM gives you. NSM, this is a quick recap on the connection setup that happens in a normal Kubernetes multi-node environment. The connection setup is done via a network service client, which is represented as a workload pod here in this picture, initiating a connection request, a network service request to its local NS manager, network service manager. And that network service manager is the thing that chooses what NSE will be serving or directly connected to that workload pod, that exact workload network service client. And the way it does that is it uses a network service registry to find all of the NSEs for this network service. And then when it decides, oh, that's a NSE on another node, it will contact a peer or basically forward the network service request to a peer. So the peer in this picture is another network service manager that is on node 2. And that's the same node where the network service endpoint is. And then the network service endpoint gets the request, fills in its connection details, and then responds. And network service managers on both nodes issue some corresponding calls to the forwarding layer, and that causes this vWire to get set up between the nodes. So if we think of, if we go to the interdomain scope, it's exactly the same pattern, the same from the client's point of view and the NSE's point of view. It's identical. They're interacting with their node local network service manager. The difference falls into what happens inside the network service manager. And the network service manager, when it's deciding which NSEs it's connecting to, it needs to be able to have a view of all the NSEs for the network service. And for interdomain scenarios, it's either configured explicitly to access a proxy network service manager, or the actual network service request format is indicating that it should try to go through the proxy. And so in the role of the proxy is to act as a peer manager to the cluster local network service managers. So this is the thing that knows which cloud environment it's in, which cluster, the cluster details, and it has the view of, is able to provide the view of the network service managers in its cluster, how they look to the other clusters or other outside world. So it's got to have in the reference implementation, what it's doing is looking for, it's basically translating the identifier for the local network service managers to the Kubernetes node objects external IPs for that node, and the corresponding port that network service manager is listening on. So we really see just a fundamental identical pattern from the actual control plane messages, but there's a proxy involved that's tweaking or mutating what's in the actual messages to reflect reachability information across cluster or cloud boundaries. So the very similar, the concept of the data plane is when I introduce that, what we're introducing is the actual semantics between the cross connect API that is local to the actual individual nodes. And so the NSM forwarder is implementing the cross connect API, and it's on each of the nodes, and then in the context where the network service manager knows how to communicate with it to provide the data plane to create the cross connect between the actual network service client workloads and the network service endpoints. So when we go to the higher level, the proxy, the interdomain scenario, the data plane model is identical. The delta here is more on what the content of the actual message in the cross connect APIs to the forwarder, and that's set up. The connection details are set up by like a layered approach where the actual each individual hop in this control plane message can provide additional connection semantics that can be consumed by the other hops and result in a data plane that's implementing a cross connect between the forwarders, as well as between IP information, or in the previous talk we showed DNS context information, but additional L3 or higher sort of connection information that is carried out by the forwarder or the NSEs themselves. And concerning the cross connect, these forwarders, when they are in their hop in the control plane capability that they have to the network service managers, and the network service manager is choosing a network service connection type or a mechanism type for the connection that both of the forwarders involved can support, and the actual parameters are set up by the serving side forwarder. So like, for example, for VXLAN, that's like choosing the VNI, right? So the VNI is set up by the serving side forwarder, and then that's communicated back through the control plane messages to the client side forwarder, and that client side forwarder will then use the destination IP that has been set up for this forwarder. So this has to have external reachability. So the forwarder has to be able to some combination of the deployment of the proxy, and the forwarder has to be able to express that externally reachable IP for the forwarder, and then the VNI is expressed as well in the is chosen by the forwarder itself and passed to the actual the client side forwarder. So then the connection parameters are in sync between the forwarder side on the client versus the server side. So that's a quick explanation of the data plane. How do NSEs get known in this system? So there's a concept that the NSM community has created called the floating interdomain or floating domain NSE registry. So what that really means is it boils down to just this idea that there's a network service registry that exists for a domain that is outside of, not tied to the cluster boundary. So you could implement this in a variety of ways, but the primary example is to have a specific network service registry that exists somewhere that's reachable by both of these clusters control plane elements, and have any network service endpoint registrations will get proxied to this floating domain network service registry. And the view of the endpoint data in these in this floating domain network service registry will be like an external view of the NSE. So the actual reachability of the NSE is going to be identified as using the external reachability for the individual network service manager that NSE is registered locally with. So in this example, the NSE is registering to on node 2 is registering to NS manager 2, and then that is forwarding the registration request to the proxy on cluster. It should be cluster 2, but it says on the right. Excuse me. And that proxy is going to mutate the registration to indicate the external reachability for NS Manager 2, and then forward that registration onto the floating domain NSR. So this floating domain NSR now has the NSE in node 2, cluster 2, node 2, and the external reachability for the external contact information for the network service manager in that same node. So in the connection sequence, I'm going to walk through a sequence diagram. It's going to be complicated, but this is also meant for being able to view offline. So we are in our node cluster 1 on the left. We have a network service client that is going to issue a network service request, and it's going to use a format that indicates that it's requesting a network service that belongs to a floating domain, and that floating domain is called nsr.foo.com, and somehow the DNS for resolving nsr.foo.com in each of these clusters has been pre-set up. That could be like a Route 53 zone in AWS, and you have, these are two different VPCs with two different EKS clusters, for example, and you've attached that zone to your VPCs. So the client indicates its network service request with the NSR domain name in this format, and the network service manager is going to do a find NSE call to determine which NSEs it can connect to. The NSR is going to notice that that's an actual not in its local domain, and so it's going to call the proxy that is local to the cluster 1, and that proxy is going to resolve the domain name and call the find network service API in this floating domain NSR. And when it gets the response, it's going to pass that all the way back to the network service manager that initiated the find of the NSEs. And this network service manager is going to choose an NSE, and that's going to be the cluster 2 NSE. So it's going to call its proxy network service manager so it can reach the actual other clusters NS network service manager, and it also calls it so that the proxy will indicate how to get back to this local cluster 1 network service manager. This proxy on cluster 1 is going to directly invoke the forward the network service request after mutating it with the cluster 1's information. It's going to call cluster 2's network service manager directly, and that's going to actually be the thing that locally binds with the actual NSE. So the NSE is going to consume the network service request, fill in its connection context information, and then set up its local resources, and then it's going to reply. And when it replies, this whole chain unwinds, and the network service manager in node 2 is going to invoke the forwarder with the connection details. That's going to fill in its connection context info, and the response back to cluster 1's proxy will come back through to the cluster 1 initiating network service manager, and then that network service manager will invoke the corresponding connection cross connect forwarder API with all of this connection detail intact. And so then these two forwarders will now have the same exact connection properties, and will operate on them to create the tunnel between the nodes in the two clusters, and concurrently they'll create the client connections to the actual, the local connections to the actual workloads, the NSE's namespace in the pod, as well as the client side namespace. So then at that point, the full cross connect is up, and the client now has a network service manager interface and a network service mesh interface and all the accompanying normal stuff. So what are the use cases for something like that? The first one we call is a private layer 3 network. So there's an idea that we could basically use this to create two sides of a L3 VPN. between in specific workloads and in specific clusters. So this use case would be really relevant for, we see like relevant for database replication or sharding. So where you have geographical reasons to have either different clouds, for blast radius or mergers and acquisitions, something like that. So we have a talk with the Vitesse project on this exact scenario where instead of just the raw database, here we have Vitesse pods, and Vitesse is a CNCF project that makes sharding and replication very cloud native, and with the proxy kind of model, and gives actually complements this NSM VL3 scenario very well. So I have a reference to that later on. But the idea is that each of these workloads just adds their annotation for a local the local identifier for the service, and then they get attached to a private network that's interconnected between clouds. So this is, we have this VL3 NSE, and that handles finding the other NSEs that are under VL3 NSEs in other clouds or clusters, and it uses a common floating registry, and it for that VL3 network, and then it will create the connection requests, and NSM will carry out the actual forwarding plane. So another use case would be if you have a specific network function cluster. So say you have a cluster, you want to have, this is kind of like the transit VPC model in, but it's adapted for specific workloads connecting to those network functions in that separate cluster or VPC. So this would be like if you have an administrative boundary between your where your NSEs, you don't want them to be actually deployed into an environment where your customers are, or your internal organizational customers are, and maybe security reasons, maybe you have some specific network function runtime environment dependencies that you want to only provide, you want to guarantee that your network functions only use like SRILV or SmartNICs, or you have some very specific things to tune your network function like CPU pinning or huge pages. This would be this would be a model that you would potentially want to use. So your client pods are just getting cross-connected with with a generic forwarder, and you have a corresponding forwarder connection into your actual network functions. So maybe like you have a slew of nodes that have a lot of different capabilities that you want your NSEs to land on specific nodes with specific capabilities, or maybe compliance requirements for security, or that you have in your network function operations criteria. So this would be a reason to do interdomain, right? Your clients are on a different cluster as your actual network functions. And then the other use case is probably the more obvious one, was like something that would maybe provide a direct connection to appliances. I think somebody had a talk about this earlier, but the idea is that your network service endpoint is really not, it's not necessarily actually in the data path. It's more carrying out the connection context and mechanism details. It's putting those into the message in the control plane messages for the connection setup, so that the network service mesh forwarder directly connects to a network function, and so that there's that's sort of like a thin layer network service endpoint that is purely speaking NSM, but also understands maybe some SDN on the back end, or understands the topology between a network service mesh forwarder and the network functions. Okay, John, do you want to take it?
Yeah, sure. So we're running a little short on time. We want to get to the demo, so I'll go through this quickly. It actually builds quite a bit on our earlier presentation, where we talked about the need for some control services, some an NSE API that we use to try to help provide those services. We're going to just show here 2 ways we use that API and 2 of the services that we require for our particular layout leading up to the demo. So if you're going to go through a little bit. So the first one here is that we need, and this was alluded to even some of the very early talks, is we need some kind of IPAM. We need, when we're deploying these services, we need some kind of, we're going to have a network between the NSEs. We know that virtual L3 network that Tim referred to. And so we have to provide some addressing information to make that happen. So what we do in this particular case is we configure some IPAM pools into a server. In our case, that server is centralized, but you could imagine distributed architectures. And then when the NSEs come up, they have a way to call into that server and request their pools. So that server is able to manage the pools and provide the addressing that provides us that layer 3 network to interconnect those NSEs. So that's one control service that we use. If you keep going, let's see. So we're just laying out the different, how the flow goes from the bar requesting or foo requesting a service to the NSE. The NSE will assign the endpoints, and you can see here we've blown out the topology of how, based on the IPAM services, how each particular application gets its addressing within the overall layer 3 scheme. In the interest of time, I'll let you look at the addressing offline and not try to go through one by one. Tim, if you want to move on. So we talked about this one quite a bit in the first talk. So again, I'm going to try to go through it quickly for those that didn't see it, but the earlier talk goes into it quite a bit more detail. But we also have the need to provide these applications, foo and bar, in this particular case, some DNS services. They have to be able to reach each other. They need to know to reach each other via the NSM networking, that layer 3 network that we set up, versus maybe a traditional CNI network. So that's the need, and this is sort of how we use that control service to handle the population.
Sorry about that.
So so Tim's jumping me along because he took up all my time. So
I accidentally hit the button, like held it down.
Okay. So here's yeah. So just quickly to wrap up. Again, we don't have much time. This is the API. It's a very simple API right now. We could add additional entry points and additional details, and it is available. That repo is a public repo. But it hasn't been, we haven't attempted to push this up to master yet, or for community to comment on. So Tim, why don't you jump on to the demo?
Sure. So like I mentioned, there's another talk for actually demonstrating this interdomain work for the VL3 integrated with Vitesse, and so that has more of the user view. So that's how more on the use case for why and what the implications are. But for interdomain, I have a tough time really breaking down what we wanted to show in the demo. So I really wanted to focus on how the connection details are set up between individual clusters, and what sort of things happen inside there. So this demo is going to show some Jaeger traces on 2 clusters, and showing how the mechanisms for VXLAN get set up. So this is in a handler for, or that side was the request side. So it was indicating like the information that it was seeing as a response from this cluster. So this is cluster 2, and this cluster has this is the handler that actually sets up the mechanism properties for chose the VNI. So this received the peer clusters information. So that control plane, kind2 control plane is the identifier, and that 172.17.03 address is the external reachable node IP for that that other cluster's NS manager. So this is where the VNI is set up, and it's shoved into the mechanism parameters in the actual network service request response. So this is the response that's gotten filled in by this local by this cluster's request handler for remote connections. So then after this happens, that's going to go to the data plane, and in this case it's a VPP data plane. So this is the VPP forwarder. This is a tool created by Andre Fabry in the Legato project to view multiple VPP instances. So this is a VPP instance on the first cluster. So cluster, the one that was actually the client of that connection we saw. And you can see in this output that there's actually 3 connect tunnels up between the clusters. So this is because there's 4 total network service endpoints in these deployments, 2 in each cluster. And so that from the point of view of this forwarder, there's only, so then that would be 3 connections across the tunnel. So each of these tunnels you can see is the first VPP calls it a destination and source, and the second one has the inverse, right, for the names. But this is all the VXLAN data that's actually this is the actual VXLAN tunnel that's brought up as a result of the connection setup parameters in the control plane messages. So that's pretty much it for the demo. I know that I could spend an hour on that demo and give a lot more detail, but that was the gist of showing what happens during the control plane. For more references, the network service mesh GitHub has an interdomain documentation with some similar pictures to what we showed in this slide deck. We'll share the slide deck as well. And then here's our the NSE that has that VL3 NSE with the network service control services API definition, and for the reference for replication and sharding, I have a pointer to PlanetScale and the Vitesse project, and there's some more talks on using network service mesh in an interdomain manner for a lot of different solutions, but mainly we have that's our executive keynote is going to be a part of that, and then we have some information on the Vitesse talks for related ideas and exactly this network service mesh VL3 integration. Okay, thank you. Sorry, Ed, for going over.
So thank you very much.
You're doing great.
Yeah, and thank you very much. So we do have a question, but we may want to take the question to Slack from Abid Ahmed. So Abid, if you can join Slack, then we'd be happy to have someone help.
On Slack.
Perfect. Great. So next up, we have Daniel Feldman from Cytail, who is going to talk about testing, authenticating, and authorizing NSM components with Spire. Daniel, you should be able to share your screen.
All right, can everyone see my screen?
Absolutely.
All right, perfect. Cool. My name is Daniel Feldman, and I worked with Ilya on this talk, although he's not online right now. It's the middle of the night for him. And the title is Attesting, Authenticating, and Authorizing NSM Components with Spire. This is a little bit of a different talk because this functionality is mostly already implemented in NSM. So we'll be talking about how it's already implemented and then what the next steps are for the future. And honestly, I'm a newbie to NSM. I've done all the examples in the repo and learned as much as I could, but Ilya is the expert, and he actually implemented Spire inside NSM. I work on the Spire project, so that's my background. So what we're going to be talking about today is service identity problems in general, and why we developed SPIFFE and Spire, sort of in a general sense, as a security tool for a variety of different applications. We're going to walk through how the protocol works, then how it's applied in NSM, and then the last subject is how do we get Spire really working for NSM interdomain, which is something that there are ways to do now, but we can make a lot better. So service identity problems in general. So you've got a Kubernetes cluster. It's running some services. Let's say they're NSM services, but they could be any other services. How do we keep hackers out? How do we keep accidental deployments from sending tons of test traffic or dev traffic to production services and messing them up? How do we prevent accidentally leaving our doors unlocked, having an ingress that is open to the public that shouldn't be? How do we make sure that none of our images or code are, have backdoors in them? There are all these different security problems, and service identity means assigning an identity, a unique identity to each service to be able to prevent these problems from occurring. So one way to do it, sort of the default way to do it in Kubernetes, is to use service account tokens, which are just JWT tokens that you can get out of Kubernetes really easily. They're just JWT tokens. Oh, sorry. So they can be stolen really easily. And also there's no obvious way to use a JWT token to set up a TLS connection. You can do it if you really want to, but it's a little bit complicated. But other than that, you could use service account tokens to make sure that each service is who it says it is. It's just a little bit clunky, and it's really tightly tied into Kubernetes APIs, which we might not want if we want to communicate with things outside Kubernetes. Can we use WebPKI to give everything an identity? The answer is no. In WebPKI, you're basically tying a website or a service very tightly to DNS so that you can prove that that website has that DNS address. And services, internal services like NSM services or some companies' internal services generally don't have well-defined host names. They might have lots of copies of a service, or they might not have DNS set up at all yet, maybe when you're initializing a cluster. Also, when a service is starting up, how would it know what its DNS identity is? So you could make WebPKI work for service identity. It's just really clunky and complicated, and I haven't actually seen it done, but this is usually the first question people ask when you say, I want to secure all these connections between different servers. Can we just do it the same way it's done on the web? And the usual answer is no, at least not easily. So what most companies are doing for their microservice infrastructure, most SaaS products or websites or whatever, they're using a secret store. They're using something like HashiCorp Vault, or there's a bunch of competitors to HashiCorp Vault. You authenticate into it and you get some secrets, and then you use those secrets to talk from one service to another service, usually just a JWT token or even just a string token. And this is actually probably fine for like a corporate network if you are sure that you can rotate your credentials regularly and make sure that they're not being misused, all that. For something like NSM, which is a product that you're deploying in lots of different places, obviously you can't really guarantee that the people who are installing and running NSM can do that. So those are a couple of different things we we really can't do. We can't easily use service account tokens to do service identity. We can't really do web PKI for service identity. We can't really do secret stores for service identity. So what can we do? Well, that's where the SPIFFE and Spire projects come in. So these are both CNCF top-level projects. They're both in the incubation phase. So we're sort of going along the CNCF pipeline where you start as a sandbox project, then you get to an incubation phase, and then you get to a graduated project. SPIFFE is the standards project where we're just trying to standardize a way to do service identity. And Spire is the actual implementation of the standard. So it's two separate projects. Well, we're hoping that there will be more implementations of SPIFFE in all kinds of different CNCF projects. It is starting to happen, but so far the only real implementation, the only real complete implementation is Spire. So SPIFFE includes a couple of different parts. These are the parts of the standard. So first of all, we specified a way to make SPIFFE IDs, which is a standard format for your service identity. It looks like a URL. So SPIFFE : // then there's a trust domain identifier, then a slash, then some kind of text identifier for your service. So that's pretty straightforward. Then we have SVIDs, which are cryptographically verifiable documents that assert a specific SPIFFE ID. So why do I say cryptographically verifiable documents? We're not inventing our own format here. We support either X509 certificates or JOT certificate or JOT tokens with specific fields filled in and certain supported configurations in terms of cipher suites and all that. So there's a way to assert your SPIFFE ID in a way that's verifiable by every party in the system. Trust bundles, which again, it's a format for your root certificates for your system. So you can verify all these SPIFFE verifiable identity documents. And then the last component of the SPIFFE standard is this thing called the workload API, which is it's a local API. It's based on gRPC for your workloads to obtain a SPIFFE ID, an SVID, and a trust bundle. And if why is it a local API is the first question people usually have. Well, if it was a remote API, you'd need some way to authenticate it. And since we're trying to solve the authentication problem, it needs to be a local API. So your workload connects to this local address running on the same node. And then whatever is implementing SPIFFE uses the operating system features to verify the process that's calling that API and give it the right SPIFFE ID, the right SVID, and the right trust bundles. And then that workload can use them to communicate. So we're not implementing a service mesh. We don't get involved in the data plane at all. All we're doing is giving things an identity. So here's, this is just an X509 SVID. This is just a dump from OpenSSL. And you can see exactly what is a little bit unusual here, which is that in this X509 subject alternative name field, that's where we put the SPIFFE ID. And other than that, it's a completely standard X509 certificate. The only difference is that one field is filled in with the SPIFFE ID. So we're sort of misusing an existing field for a different purpose. And other than that, it's completely compatible with all your usual TLS libraries. You can use it to initiate connections. You can use it within proxies. You can use it within web servers. You just need to maintain that, that one field. So how do we start up a Spire system? Well, first of all, you have a Spire server. And in a typical, like a corporate SaaS environment, the Spire server would be running on maybe separate hardware, maybe some kind of trusted environment that only a few people have access to. For NSM, it's running on the same Kubernetes cluster as everything else, which makes sense for the threat models that NSM faces. Because if someone can get into your Kubernetes cluster that's running NSM, they already have access to all your data anyway. So it doesn't matter. But in a company that maybe has 1,000 developers with access to Kubernetes, you want to keep your Spire server separate because that's signing certificates that everyone else has access to. So you start up Spire, and then you install these Spire agents, they're running as a Kubernetes daemon set on each node. And the first step is something called node attestation. So we have to authenticate each Spire agent to the Spire server and the Spire server to each Spire agent. And I'll go into how that works in a minute. It's not any kind of big mystery. You can use a join token. So you're basically just copying and pasting a string. You can use Kubernetes features to automatically do this, which is what you do in NSM because it's always running inside Kubernetes. There's a couple different options there. Then once you have the Spire agent authenticated to the Spire server, you can set up workloads, and each workload is talking to the Spire agent. The Spire agent is talking to your operating system, verifying the identity of that workload and giving it the right SPIFFE ID, the right trust bundle, the right SVID. And it can talk to the Kubernetes API, make sure that it has the right image, make sure that it has the right pod name, make sure that it has the right service account name before doing that. Then once everything has an identity, either a JOT SVID or an X509 SVID, then those workloads can establish secure communication between each other. And again, we don't actually tell you how to establish the secure communication. You can do that with TLS gRPC, which is what NSM is doing. But you could also use any protocol you want that you have some way to use those identities for. So I did a little more detail on how the node attestation setup works. So this is how the Spire agent gets its identity. The first step is, first of all, you need that trust bundle initially, because otherwise the agent would have no way to trust the Spire server. So you have a trust bundle that's stored somewhere in NSM. It's in a Kubernetes config map, but we also support all kinds of other configurations. You can have it in S3, you can have it on just in a file on disk. So you fetch the root certificates. Then the Spire agent talks to the Spire server and requests its own node identity. Assuming you're running on Kubernetes, the agent requests its identity from Kubernetes. It gets a signed node identity. So for Kubernetes, it's a service account token, which is cryptographically verifiable. It sends that identity over to the Spire server. The Spire server verifies the signature. And then repeatedly over time, the Spire agent is sending a CSR, is sending a CSR to the Spire server. The Spire server is signing that CSR and sending back a signed SVID and a trust bundle. And that happens very frequently, typically every few minutes. It's at least checking if the SVID needs to be refreshed. And in our standard configuration, the SVID is refreshed every 4 hours. So these aren't long-lived credentials. They're refreshed really frequently. Usually don't need to have ever revoke them because they're just going to expire on their own really quickly. And then workload attestation. This is the step where the Spire agent figures out who's talking to the Spire agent to get the SVID that's actually used for communication between services. So first you need some configuration. You need something called a registration entry, and I'll go into that in a second. But that contains sort of instructions for the Spire server on which workload should get which identity. And then again, repeatedly over time, the agent is connecting over to the Spire server, and it gets a list of the registration entries. It makes up some CSRs. The server signs those CSRs, and then the server sends back SVIDs. And then frequently, again, every few minutes, the workload gets new SVIDs, and that's updated through a gRPC API running over a local socket. And again, it needs to be a local socket because the workload has to be able to identify itself to the Spire agent in a secure way. So we use features of the OS kernel to verify the process ID, the group ID, the binary that's running in order to give it the right SVIDs. So where do these registration entries come from? So again, the first step in configuring all this is you need these registration entries. in a typical, like a SaaS company that's running 1,000 different services, you'd probably have some security team managing all the registration entries. For NSM, because it's a prepackaged product, that obviously doesn't work. So instead, there's a sidecar proxy, or sorry, just a sidecar called NSM Spire that takes a bunch of JSON registration entries and just loads them into Spire every time that NSM starts up. And you can find these registration entries. They're in a JSON file that's checked into the Helm chart for NSM. And all it's doing is it's assigning a SPIFFE ID. So this SPIFFE ID, oh, that's actually for Spire itself. But here's the SPIFFE ID for NS Manager. It's assigning the SPIFFE ID NS Manager to the Kubernetes service account NS Manager account. So any service that's running under that service account can get this SPIFFE ID. That's all it's doing. And this is a really cool way of doing it, loading the registration entries in from a JSON file automatically. Again, most of our users are, maybe at a company where there might be hundreds or thousands of services, and there's someone sitting around managing these registration entries for all those services. But because NSM is a prepackaged product, they're just stored in a flat file and loaded in. Now, interdomain is where it gets really interesting. Obviously, NSM needs interdomain to really be useful, and this is still in the early stages for SPIFFE. In a typical company, again, a company that would just have one big Spire server, they might have 10 different Kubernetes clusters or 100 different Kubernetes clusters, all talking to one Spire server that's sitting in a server in their data center somewhere, or sitting in one enclave on the cloud. So they don't need federation quite as much between different domains. For NSM, because the entire point of NSM is to establish network communication between different Kubernetes clusters, you really need federation between multiple Spire domains. So you would have one Spire running in each Kubernetes cluster, presumably, in a typical NSM setup. And federation between Spire domains, we do have it working. We actually have a couple different methods. We don't have a whole lot of documentation on how to do this, and configuring it is still a little bit complicated. For the NSM examples and the tests that are checked into the NSM repository, they're actually using a little Go proxy that just provides a SPIFFE certificate, sort of going around the node attestation API and the workload attestation API, which is a really clever way of doing it. But in the long term, what we really want is either two different Spire servers exchanging their trust bundles frequently, so they're basically federating independently on their own, and then each Spire server would provide SPIFFE certificates to all the services running in its Kubernetes cluster, and then they'd be trading bundles, so they'd each trust each other's certificates. Or another approach that is sort of complementary would be having an upstream Spire server that's signing root certificates for two other Spire servers, and each Spire server is providing certificates for everything in its Kubernetes clusters. And then because they'd all use the same root certificate, they'd all be able to trust each other. So again, this is still a little bit of a work in progress. It's really important for NSM, and we understand that. It's for a typical company that's just got one Spire server or one cluster of Spire servers, it's probably less important because they don't necessarily need to establish these federation relationships. So the ongoing work that I'm working on, and that the whole Spire team is working on, we just finished a big project where we refactored all these APIs, made them a lot cleaner, a lot easier to understand. Improving federation is a top priority, like I just said. Improving JOT support. So we do support using JOT tokens as a SPIFFE identity document, but it's not exactly documented very well, and we're going to do a lot of cleanup in that area. Transitive identity is a huge project that a lot of people are working on, including some people from the NSM project, but that's basically using a separate identity from some other system and passing it through SPIFFE identity. So I can verify that my name is Daniel and I am using SPIFFE service X and pass my identity as Daniel through the SPIFFE identity in a verifiable way. So that's a huge area of sort of ongoing work. Another thing that isn't on here that we're working on is federation with OIDC identity providers. So you'd be able to use your SPIFFE identity in order to connect to, say, the AWS API. And that's actually pretty much working, but again, the documentation is a little bit lacking and it's a little bit clunky to configure. So that's just about 25 minutes. Thank you very much. Here's all my contact information, dan.feldman@hp.com, Twitter, Ilya. You can follow up with him on some of the details since he did a lot of the implementation of Spire within NSM. We've got some other talks on Spire on the Kubernetes KubeCon maintainer track. They're actually both tomorrow, and you can look on the schedule and get the time in your local time zone. I'm doing one, and then Andrew Harding is doing maybe a more advanced Spire session that might be really useful if you want to get more into the details of how Spire works. We're on the NSM Slack. There's also a SPIFFE Slack channel. And I guess we have some time for questions. So it looks like I got a couple questions on Slack, which isn't coming up for me right away. Sorry. Where'd my Slack window go? Okay. So we had a question, is Istio SPIFFE compliant? And the answer is they're working on it. And that's why I said it's sort of work in progress, getting more different service meshes to adopt SPIFFE. It is not fully compliant yet. It doesn't support the workload API. And we have proposals out to them to implement the workload API, basically. Next question is, can we point to documentation on Spire Federation? I will follow up offline on that. We have some stuff in progress. I actually wrote a blog post about a year ago on how SPIFFE Federation worked, but that's a little bit out of date. That was a year ago. Like every open source project that's changing very fast, the documentation is always a work in progress. Are there any questions on the Zoom session? All right, great. So I'm at exactly 29 minutes. So I guess there's we can go on to the next session. And thanks everyone, and follow up with me on email or Slack or Twitter or whatever is most convenient for you with any questions. Thanks.
Great. And just so you know, John Joyce had a question about where to find documentation on SPIFFE or Spire Federation work in Slack. So if you could follow up there, that'd be fantastic.
Yep, I'll follow up. Thanks.
Thank you. So next we have Ivana from VMware, and she is working on traffic visualization solutions for NSM. Ivana, can you share your presentation, please?
Hello. Should I start 3 minutes earlier? Or wait until it's 7 my local time?
Yeah, I think it's okay to get started. So chances are we'll have someone else who goes over a little bit longer, so it'll average out well. Thank you for asking. So you should now have permission to share your screen. You've been set as a co-host.
Yeah. Do you see my screen now?
Yes, we can see it.
Yeah, just a second to. Okay, so hello, I'm Ivana Tanasova from the Network Service Mesh community. And in this talk, I'm going to share with you our community efforts for visualizing the network topology with NSM and also the traffic that is going between the different endpoints. And to start with, let's say how the traffic is represented in a point-to-point connection that is created by network service mesh. Once the client and an endpoint start to talk with each other, they receive and transmit bytes packets, and which we represent by RX and TX bytes and packets. And we also have RX and TX error packets, which are actually the dropped packages in that communication. And this is so good, but you may ask how you can actually observe those and how you can see what's going on with your connection, what fails to be received. What we have by now, we did an integration with Prometheus, which presents metrics for all those transmits and received data. In the diagrams that I show you, I used 4G LTE network example. It's located in the examples repo. The example generates some traffic between the different clients and endpoints in it. And this is the traffic that you actually see. In Prometheus, we have vectors for RX and TX, bytes, packets, and error packets. And in order to observe specific connection, you need to check a vector, for example, the TX bytes. In this example, you see the transmit bytes between the packet gateway and the PCRF. In this example, you see the TX bytes between MME and HSAS. I also added examples for the RX bytes between those. And as our 4G network example doesn't generate any error packets, this is why this diagram is empty. But if in your use case you have some drop packages or other problems, you will be able to observe them with the error packets vectors in Prometheus. Yeah, this is a good way to visualize traffic that we have by now, but we want to have something even better than that. Some good and interactive way to see the whole network topology and what's going on with the connections. We found a project in GitHub that looked really cool. And we very much wanted to have that visualization for NSM and to see in such a good way all the network that we create and to see all the packets, to can check them specifically, to have statistics. And we tried to integrate with that project, but this way what we actually, where we actually reached. It doesn't look as in the example. And the reason for that is first that the project was abandoned since 2 years, which we actually missed to check in the beginning. And it has some issues that weren't resolved since those 2 years, which were blocking for us. And in the beginning, we started to try to resolve them on our own. We thought that it will be simple, but new issues appeared when trying to get the project up to date. And it came out that it's really hard to estimate how much time and effort this will take. And the more serious problem is that if we fork that library and fix everything, we will need to support it in future, and to have one more project to support, just to go on with NSM in order to have that visualization, to always update all the versions. And it didn't look very efficient for us, even though it looked pretty nice. And we very much want to have such good visualization. But this is what inspired us to think in that direction and to search for something else. Someone presented about Kiali in our community meetings. And we liked this as an option. It is created for service meshes, and this is one of the reasons we also like it, because it's widely used in Istio. It has several benefits: that it's interactive, it has good topology representations, you can observe traffic, there are some validation options within the project, it provides metrics, but it also, when we investigated the project and what we can do in order to integrate with it, we had some problems. The first is that it is very tightly connected to, it is created for Istio, and it's not abstracted, so that you can easily use it for another service mesh. Everything within the project was specifically created for Istio. We found out that there is a team within AWS which integrated Kiali with Linkerd. I contacted the person who did that integration, but he didn't work for that team anymore. And then I contacted the team and tried to make some collaboration. I couldn't actually reach out, so that it came that if we choose that, it will be our own effort, and we cannot exchange experience with other teams. At least we didn't know about any other team at that point. We estimated that it would take a lot of time to do that, and we need an agreement from the community, or we need to do that on our own on some fork, which is actually not a good approach in open source. So in order to use Kiali, we need a good proof of concept. What we mean by that, we need to see that there is a community strategy within Kiali to decouple from Istio, which wasn't visible at that point. And we wanted to make sure that this is a project that will be alive and supported for a long time, that it has a wide adoption, or if it doesn't have at the moment, that it's working in that direction, and it has some signs to be used from other service meshes. And I shared those ideas with the community and get some feedback about the Grafana plugins, the diagram and flowchart plugin. There are two plugins that are actually good for our use case. We did a representation with them, and it looked really nice in terms of the topology. It shows the vectors, the traffic that is going on, but it also has some problems. The biggest problem is that all that diagrams that you saw the graphs that you saw, they were created by hand. They actually need a predefined topology that you write for those plugins, and then you run Prometheus, and then you get the data. And this is not very efficient because you need to do that for every different use case. Here, there is a good solution. If we implement a network topology CRDs that describe the topology, we can use them, and we can easily integrate. We can write an automation that converts those CRDs to a format that is readable from Grafana plugins, and we can automate the process and have the diagrams. But this is something that is maybe a good solution to look at in future. Not yet available, but is still an option. I also received feedback from Matthew Rohan from our community. He shared about this Hubble project. And it looks really nice, lightweight. It's easy to run. It is exactly what we need because it represents topology, and it shows the connection, and it shows the traffic that is going on between them. It shows all the failures and all the information that we need. We run that for, it also has good charts that are that can be used to observe the traffic, and we try to run it with our 4JLT network example to see how if it works for NSM without any additional efforts. It creates the network easily, but it failed to recognize the connection. Then we reached the Hubble community. We created an issue, and they pointed out how we can easily resolve that problem. So in order to have a representation with Hubble, we can have a pretty simple fix with NSM so that the connections will be recognized by Hubble. The project looks good. It has everything that we need. So it seems healthy. What I mean by healthy, it's active. They respond pretty fast to issues. It looks well implemented, and there are not actually any concerns about using Hubble. This is one of the best options, in my opinion, to integrate with. What else we have? We have Skydive. This is a project that we already use. It represents it visualizes the Kubernetes cluster and all the pods that are created in our network. And it already supports traffic metrics. But what is the problem with them? It represents the metrics that are represented with Skydive are between specific network interfaces, and the network interface is not something very human readable, and not a good way for a person to to check a traffic between specific endpoints, because you need to find out what the network interface is, and it's much better to have that metrics data between specific pods. So for that, we opened an issue in Skydive to form a discussion with their community and share what we want to have. And we have several options. One is to at our metrics that we have, different from the metrics of the network interface, is our vector representation. We can add them to the Skydive UI, or we can implement a separate Prometheus probe that takes all the data directly from Prometheus, represents the network topology, and show all the data. The good thing is that Skydive is already integrated with Network Service Mesh, so that if we use that, we will have the same solution, but we'll have some additional data with it. So it's pretty nice to have that. So what's next? What we need to do in that direction? For the visualization, we need to choose a project from the listed solutions, or maybe if some new and really great solution comes, and we need to write an integration about it. We also need to update our metrics to support the path concept and to get up to date with the cross-connect, the new cross-connect API. And one of the goals of this presentation is to check with the community and anyone interested with NSM what you'd actually like to see, how what you need in terms of visualization, what are your preferences and needs, and anyone that is also willing to get involved in that effort, you're welcome. We are open for questions, for any shares, ideas, feedback on this. And yeah, we want to thank to the sponsors of the event. And with that, I'm going to say thank you, and I'm happy to hear your questions.
Thank you very much, Ivana. So next up, we have a cloud native WAN, a cloud native WAN for microservice applications. So we are running a little bit early right now. Ed, what's your opinion? Should we take a little bit of time now? We do have a break after this, but we are running about 15 minutes early.
I'm fine either way. I guess we can. I don't know if there are opinions from the next presenters up.
So for us, it's fine, Ed. I mean, if you ask me, I would say maybe let's wait now, so we start at the time, just in case that people that check the agenda and are interested into the talk, that are going to connect right for the talk, can take a look. But either way, it's going to be fine with us.
Maybe, Ed, we can start 5 minutes early with the scheduled time, so if people join, they don't lose a lot. And
okay,
makes sense.
Sounds great.
In the meantime, we could also take a few questions as well, because I know that there's been a lot of material that's been shown and published. Is there anything that anyone would like to ask? And you can ask through Zoom, or you can ask on Slack, and we can answer a couple questions. Give people a few moments. Tim Swanson just asked if we had ever thought of exporting the data to a graph database or time series database to build a visualization on top of. So Tim, I personally have thought about exporting it to a graph database, but I haven't taken any steps to do so. I think it's a fantastic idea. Graph databases, I have experience working with them in the past, and they certainly have some very interesting properties in terms of modeling and human interaction that you can get into with them. So if you have any ideas towards that, we would love to see them presented in the community moving forward.
Yeah, I think I've seen a few teams at Cisco do some stuff with Arango DB, and I thought the sort of time series aspect, like for playback of changes, was really, really awesome. So I thought that might be pretty cool.
Yeah, and there's a couple ways that when you start to look at graph databases and time series databases, like they're certainly two separate things, but when you pair them together, they give you a lot of flexibility in terms of how you read and model your data. And I think it'd be quite interesting to see both of them paired up, like maybe having something similar to having the time series embedded as part of the model would be an interesting way to efficiently expose and track and expose some of the information. And what tends to happen in cloud native is that you have a series of events that occur, and those events could be log messages, they could be metrics, they could be tracing messages, and we tend to try to think of them as a generic event. And of course, you could specialize the event based upon the type of information it has. But by treating it as an event stream, then this means that you're able to stream it towards something like FluentBit, or you can stream it towards something like Prometheus in order to visualize it. And it also means you can bring the right tool to the system, so that perhaps one system does very well in terms of logging and showing off how logs work. And you look at something like Jaeger is fantastic with gathering and tracking, tracing information and presenting it in one spot. And so giving that central place where you can then build other tools on top of with something that's designed, specialized for that use case is definitely something I expect to see happen. We also have a comment from John Joyce. He said, Tim and I showed some use cases and would love to be interested to hear if anyone in Zoom has interested in any of those use cases or have some of their own. So, John, I can tell you for sure that the use case that we showed off in the keynote has a very strong need for the virtual L3. And to give you an example, when you're working with very large companies, and so not necessarily Anthem, but it's something that plagues most very large enterprise companies, is that the time to integrate to integrate a partner or a client, if you need to pair up some form of VPN, can be very expensive. Like, it's not uncommon for some of these types of engagements to take months, or in worst case scenario, quarters, because of the way that policy is set up, the way that policy is managed, the way you configure your change and manage your change in those systems over time. There's a lot of information to deconflict, and even with the best planning, all you need is one merger in a company to bring in their network, to throw everything in disarray and have to redo all this stuff over again with long cycles. And so having some form of a virtual L3 would allow us to abstract that kind of relationship, gives a very clean contract. And the reason that I think NSM really shines in this particular scenario is because we've taken things that were historically global, like you take an IP range or a set of CEDARs. And instead of saying these things must be global, we can never conflict with them, and we have to track these things at a global level, then this allows us to get away from keeping those things in track in that specific way, and instead allows us to localize those problems. And so we can say, is my current workload and your current workload that we're talking about, can we find anything where it just doesn't conflict between the two of us? We don't have to worry about the rest of the world. And in fact, I actually expect link local addresses to be very useful here. And for those who are unfamiliar with link local addresses, you can think of them as addresses that are designed for point-to-point connections. They're actually specified in an RFC alongside with the private networks as their own range. And they're designed for when you plug in a system, if you don't have DHCP and you see a 169 address pop up, that is usually a link local address. And so these things are considered to be non-routable on the internet, but they're perfectly fine to use in a point-to-point connection. And when you're only dealing with workload to workload, then they tend to you're able to reuse them and not worry about that conflict. So in short, yes, there is a strong use case for the interdomain use case between multiple companies, coupled with the work that Daniel showed earlier with the interdomain, and I believe that'll be a very powerful feature for many.
Yeah, I recognized right away that the Anthem fit into that, and it's kind of interesting. I was just about to ask you, well, don't you see the federated SPIFFE work being key to that too? So you kind of beat me to it there. So that's why I had so many questions about the federated SPIFFE, because it seems like it's like hand in glove kind of functionality you need for that use case.
Absolutely, and take it a step further. When you mix in, we didn't talk about policy recently, but when you add in policy, the policy can be declarative, and it can be based not on you could base them on IP addresses, but we have a higher level thing that we can bind against. We can bind against SPIFFE identities. And so this means that we can actually look at these identities and say, is this identity allowed to connect to this secure corporate internet? And it doesn't matter what IP addresses get assigned, because we're able to identify the workload programmatically. And this ends up eliminating a lot of issues where, like, when you start to do these things, like create your network access control lists, then you tend to have to put the IP in port, and you have to keep very close track as to what's being assigned where, and how does this change over time. And in fact, it can actually be very scary to deprovision a firewall rule, an allow rule, because it's not uncommon for developers to say, "Oh, this thing's open. I don't need to put in a change request." So now you have a hidden link there that wasn't reported because it just worked and they had that path available. And so in this scenario, we could actually create policy that is declarative, that says this workload can communicate to that workload in this specific way. And that means when you deprovision an application or deprovision a feature in an application, you remove that from your policy, but your policy for each application is rendered for that application. So you can change things without worrying how you're going to interfere with other applications. So when you bind against these three things together with NSM virtual L3 coupled with identity and policy, you have something that's very powerful that allows you to control your network, not just from an L3 and L4 level, but L7 with policy to say, like, what type of HTTP messages or gRPC messages are allowed to be put down, and drive that all the way down to L1, where you could even have a policy that says this particular thing must have this certain TPM module that outputted this particular type of information we can verify, so we know that only our systems have made it onto are making it onto the network, things that we have personally vetted ourselves through our supply chain. So it allows us to create like an identity cube effectively that covers L2, L3 across the organization and up and down the stack. So.
Yeah, and I think Fabio is probably going to touch on some of that same policy talk, right in the next few minutes here. But yeah, I see it all coming together.
Cool. And with that, we should probably get started with the talk then. So we have cloud native WAN, a cloud native WAN for microservice applications. And with us, we have, and apologize for the names if I don't pronounce it properly, Fabio, and is it Laurent?
Yeah, my name short is just Laurie, so it's easier for everyone.
Okay, Laurie. So we have Laurie and Alberto. So Thank you, and you all have the floor. And let me know if you have trouble presenting, and we'll get you the right permissions.
All right. So, okay, let me see if I get something right. So now you should be seeing my slides, I hope, and the right screen, I hope too. Is that right?
Yeah, it looks good.
All right. Okay. Yeah. So as you know, we actually have the whole team here. So it's not only Lori, Fabio, myself. We also have Ellis and Jordi in Zoom and in Slack. So the whole CN1 team is here eager to answer your questions. Yeah, so we are going to talk about cloud native SD-WAN or CN1 for short. We are a team of people that we are part of the IBM CTO team at Cisco. And we have been looking for a while at the intersection of Kubernetes with a bunch of different IBM technologies. And one of the things we have looking at recently is SD-WAN and how SD-WAN can better serve Kubernetes. So today we are gonna talk about briefly about who are we and present a bit the team. Since we have extra time, we may as well use it. We're gonna go through the cloud native SD-WAN overview. What is it? We just released the code like literally 2 days ago or so. So it's super fresh. Probably is broken at this point. So good luck, guys, if you try to use it. But we will improve it over time. It works for some POCs, so it should be all right. And then we're gonna talk about CN1 and NSM. And yeah, we are not really experts of NSM, unfortunately, but we have hear a lot about it, and it's a project that really fits well with what we are doing. So we saw some synergies there, and you'll see in the presentation why it was so clear for us that there are some synergies there. So we hope that there is a possibility for integrating the two here, and we'll go through that. So who are we? So this is the whole team here. I thought it was funny to put the people in the map because this is part of KubeCon Europe. And at some point when we were preparing the slides, we realized, oh, we are all from Europe, at least originally. So it's a funny thing that CN1 is introduced in KubeCon Europe. So yeah, in the presentation, it's going to be mostly Lori and myself talking, but you can see there the full team. You can see both Lori and myself there in the bottom right. Really happy, I guess, that there was some video involved in that picture, either before, after, or during. Yeah, and our background, like for the whole team, is mostly on networking and network virtualization overlays and so on. Some of us have done some Kubernetes in the past, so yeah, we were trying to put the best that we know here in the project. Okay, so let's jump to cloud native SD-WAN. So this is how. Maybe let me take a step back, and I'm assuming always that SD-WAN is something known by everyone, but that may not be the case. So software SD-WAN stands for software defined wide area networks, and this is a trend that has become popular across the industry. There are multiple vendors that are offering SD-WAN solutions nowadays. That is basically optimizing WAN connectivity, right? Taking advantage of SDN, software defined networking principles. You can be smart on how you handle different tunnels and connections over the internet or private links or have you, and you can render better performance for the flows. Now nowadays is somewhat common, or to some extent common, to have Kubernetes clusters that are consumed by either user or other workloads that are remote, that are not right there with the cluster, right? And in some cases, the connectivity we need to goes through an SD-WAN. Even if you don't notice it because you are just connecting to the cluster, there may be some SD-WAN that the enterprise or whoever is handling the infrastructure has deployed that optimize the connectivity towards the cluster. In the presentation, we tend to talk about how a NetOps team handles the SD-WAN and a DevOps team handles the the Kubernetes cluster, but I mean, bear with us on this one. These teams can be the same team. Also, maybe it's not appropriate to talk about DevOps team because DevOps is a set of practices and so on, but I guess that we can be more or less on the same page here. And the point that we are trying to make here is that, sure, you have the two, you have SD-WAN and you have Kubernetes, and maybe the traffic for your Kubernetes workloads goes to the SD-WAN. But today the two are like ships in the night, as we say. So they are both there, they both exist, they do stuff nearby each other, but they have no idea that the other one is there. So anything that you want to do today goes through some manual integration. So people working on Kubernetes or people working on SD-WAN, they talk with each other and they find a way to make the things work better together. And as we know, all that manual integration is something that we all love. And Jan, apologize for the bad memes that you're going to see through the presentation. So we said, okay, why don't we do something better? Why don't we add some SD-WAN here, some CN1 here to the picture? And that's what this presentation is about. We want to talk to you about an integration that we have done between SD-WAN and SD-WAN in general and Kubernetes and the different components that enable it. And then how, when you have not only Kubernetes and SD-WAN, but also NSM on the picture, how CN1 can help there as well. Maybe something that I should mention, and I should have mentioned before, is that when we talk about this with people and they hear cloud native SD-WAN, they think that this is about an SD-WAN that is composed of cloud native pieces. I mean, it may be, it may not. What this is about really is how to make an SD-WAN, any SD-WAN, cloud native or not, aware of Kubernetes. So when we talk about cloud native SD-WAN and CN1, it's all about making any SD-WAN aware of Kubernetes. So with that, let's jump into the architecture and you see what this is about. So basically, this is a bunch of magic that we have put together, but I guess that you want to get some more details. So let's go to the boring squares and diagrams and arrows and whatnot. So let's start from the beginning. You have a Kubernetes cluster running some services, and then you have an SD-WAN controller that is controlling your SD-WAN. Now, if we were to do what we do today, we will stop here, and then we let these poor guys on the left side and right side to talk with each other and try to do something about it. We are trying to do better here. So what we propose is that by annotating the YAML file on the service, and all of you in the NSM community, I'm sure that are really familiar with annotations on YAML on Kubernetes. By putting some annotation on the YAML on the service, we can specify the WAN needs for a particular service that is exposed in the Kubernetes cluster, right? And the YAML annotation is not a fixed format. We have some ideas in the code, and if you go later on to the GitHub, you'll see more or less what we use. But it's basically anything that we can understand as, okay, this service is telling us this is what it needs out of the SD-WAN, or what the service is doing and how the SD-WAN can help the service to deliver better. So the flow starts with a DevOps person putting an annotation on the YAML file, specifying some SD-WAN metadata. Now we have a component that we call the CN1 operator that is extracting that information out of the service. So it's constantly checking for annotation in services that have anything to do with one operation and extracting them. And once it detects some of that, it goes to a service registry and puts information there. And this can be any service registry. For instance, we have a demo in the Cisco booth about CN1, and we're using Google Service Directory for that demo. But this can be, for instance, DNS, right? DNS is a good example of a general service registry. So as long as you can put this in a service registry, you should be good to go. And then from the service registry, we have another component that we call the CN1 reader that is getting the information. As you see, this is more on the SD-WAN side, right? So we have like components that go more on the Kubernetes side, components that go more on the SD-WAN side. So the CN1 reader is extracting the information from the service registry. So it's polling. I mean, you can have some PubSub model as well, but the code that we have, the initial code is just polling a given service registry and learning about services there and one annotations on the services. And then we have the SD1 adapter, and this is specific for each specific SD1 solution that you have. So if, for instance, you're using Cisco Viptela SD1 as we use in our demos, you will have an adapter that is for Viptela. If you have any other SD1 from other vendors, you are going to have an adapter for that SD1, but the concept is general node, and the code that we have in the adapter, we hope it should be general node that can be adapted. And actually, we're looking at having more adapters for other SD1s. So the SD1 reader passes information to the adapter, and it's basically telling the adapter, hey, I see that through the service registry and so on, I see that this IP and port is for a service on Kubernetes, and it has some particular SD1 needs or one needs. So please take care of that. And in general, we call the SD1 reader and adapter the SD1 adaptation layer, because we see that as how you adapt this for the SD1. So then what is left is that the NetOps person is to configure the SD1 in the way he or she wants to, right? So that the SD1 does something for that kind of metadata. And also you need to map the policy with the metadata. So you can define some policies on the SD1 controller. Let's say, I don't know, you can create 2 different tunnels with different latency parameters or different types of encryption or different bandwidth available to them, right? So you can create different policies, and then what you do is you tell the SD1 adapter, hey, when you see metadata for this particular kind of metadata, right, that you have extracted all the way from the YAML file, when you see this particular type of metadata, I want you to put this associated with the policy that I have created in the SD1 controller. And eventually what the adapter is doing is configuring the controller so that the services that belong to that are tagged with that metadata can be enforced the policy that the NetOps person has done. And that's wonderful, and it works, and we are very proud of ourselves for building this architecture. I mean, it's kind of what you do when you start looking at these things is what comes out naturally. So let's go through an example, and hopefully, if things don't make sense, will make sense in a second now. Here we have the components that we just discussed with a bit more, space, because we're going to populate that with examples. So we still have the operator on the Kubernetes cluster. We have the reader and the SD1 adapter on the SD1 side, and then we have the SD1 controller, and then we have also the people involved in this picture. So the example that we are using is a video conference application running on Kubernetes. We use this example because it's easy to see different microservices, right, that may belong to the same application as large. And each of these microservices may have different needs. So in a typical video conference application, you're going to have voice, video, slides, chat, and you can imagine others as well. And you can think that each of them may have different requirements in terms of the network, what they need out of the network, especially when you're connecting to this service over a long distance link and so on. So what you do on the network may be relevant for each of these microservices. So if you do nothing and you just establish SD1 connectivity to the cluster, things will work to some extent, and you will have some connectivity, I hope, if the NetOps guys are doing the right thing, and usually they do. So you're going to have some sort of connectivity there. Now, how we can make this better with Gen1? So the first thing is that you need to establish which kind of metadata you're going to accept, right? And this is what the NetOps person is doing here. It's configuring the adapter, saying these are the kind of metadata attributes that are relevant from the point of view of SD1. So if you annotate your services, make sure to use one of these attributes, so I know what to do with that. And the NetOps guy also populates the SD1 controller with different policies. And here you can see this very simplistic example just to convey the message. But the NetOps person is basically going to the SD1 controller, configuring 4 policies in this case, and then those policies are mapped to the metadata attributes that they are in the adapter. So you can see the policies, and these are typical SD1 policies, like, okay, for instance, for real-time traffic or for real-time services, I want minimum latency, and I care that you don't drop anything on the SD-WAN. And SD-WAN has features, many SD-WANs have features that can do forward error correction and so on, so they avoid dropping packets. At least they give you the illusion that they are not dropping packets, right? Or for instance, for streaming, what you care about is having a lot of bandwidth and latency, and if you have some drops, that's okay. Usually, and then for file transfer, you care about the bandwidth and having no drops. But I mean, if the thing takes a bit more time, that's why fine as well, and the best effort is best effort. So you do what you can, and then also that it gives some freedom to the network administrators to allocate the flows in maybe in links that are not as well behaving as the others. So they have some room to play with. So with all this in place, now the DevOps knows what kind of labels or attributes they can use. So that's what we are doing on this part of the example here. The DevOps team is going to the application of the cluster and annotating the different microservices with these attributes, right? And you can imagine, voice is real time, video is streaming, and so on. And we are just using the real time streaming as examples. Here you can put anything. So if you want to, to say that the metadata that you care about is called something else, you put that, and you just need to configure the system so it makes sense for you. When we talk about this with people looking at deploying, CN1 for prototypes and POCs, usually what they tend to do is to have some defaults and then have some more specific ones. But I mean, you can make it as you want here. Then the operator is monitoring for those attributes. So the moment you put them on the YAML files, the annotation, the operator is gonna notice. And we had a good talk about operators early on, so you got the idea what the operator is doing there. So the operator gets the annotations, goes and registers them on the service registry, and then the CN1 reader can get the information. Basically, the CN1 reader is getting, hey, I have this service voice that has been annotated with real time. So it passes all that information to the CN1 adapter, and the CN1 adapter then to the controller. So you end up with this. So you have this service voice. And again, the service voice comes with the IP address and port usually. So the SD-WAN knows which packets belong to the service voice, and that they are getting from the Kubernetes cluster, right? So if the 4 microservices in the example are exposed externally, either through load balancer, node port, or whatever you want to do there, you're going to get the external IP address and port that you can get to reach these services from the side of the cluster. So the SD-WAN can see traffic going to those services and can optimize the traffic based on that. And that is the information that is now on the top left. That for this IP address and port that represents the voice service, I want you on the SD-WAN to enforce a policy that is about low latency and minimizing drops. So with all that, the gray tunnels become cheerful and colorful tunnels, and life is good. So with that, we jump to the CN1 and NSM integration. And here we would like to pass the ball to Lori, and maybe we can share the slides through his laptop so he can also click on the animation. Can you share on your end, Lori?
Yep.
All right. And we see them, perfect.
Okay. I am now going to go a little bit overview of NSM, which everyone is probably quite familiar with, and how it integrates with the CN1 solution that we have been worked on. This is the typical NSM deployment where we have 2 different service manager domains which need to communicate with each other. In typical enterprise use cases, this one side will be a data center of the enterprise, and the other side will be a branch, for example. And there will be several branches depending on how the enterprise wants to develop its connectivity. And the reason I talk about an enterprise is that typically enterprises are more likely to deploy an SD-WAN. So the virtual wires between the NSM forwarders will be able to take advantage of all the features and advanced connectivity management that an SD-WAN product can offer. And in order to avoid the ships in the night problem that Alberto was mentioning, here is where we give this architecture a pinch of CN-WAN, which will be the link between the network service registry and the SD-WAN controller. And I will get into the details of the integration right now. So the CN-WAN part was what Alberto presented up until now, where we have this reader component getting information about services and an adapter that talks to an SD-WAN controller, and this adapter needs to be different and written specifically for each product separately. And this we call the CN-WAN adaptation layer. On the other side, we have a network service registry domain where we have the network service central registry and many, potentially many network service manager domains. So the link and the integration between the two will be this represented by this arrow, where the CN-WAN reader is watching changes and reading information from the network service registry. And based on the metadata associated to network service endpoints, it can then install the right policies into the SD-WAN. So to make this a little bit more palpable, let's take an example of Telepharma Company. Telepharma Company is deploying these kiosks in different pharmacies where users can interact to order, for example, pills, to do some basic health checks, maybe a bit of very basic telemedicine and so on. And this Telepharma Company kiosk is running Kubernetes in this system. It is installed and it is connected to an SD-WAN network operated by the company or by the network of the pharmacies where these kiosks are deployed, and takes advantage of both network service mesh and the SD-WAN that is deployed to optimize the different microservices that is being used by this application. So you have the Telepharma headquarters, where you will have all the central application, the data and everything. And then you have several kiosks that will connect to this headquarters. You have NSM installed in each of these kiosks, and a network service endpoints for the different types of services installed in the headquarters. And then all of this is a single network service registry domain, which will be taken advantage of. So these network service mesh forwarders will be connecting to the headquarters using the regular virtual wires. We'll have a different virtual wire for different microservice applications running on this kiosk. And then these virtual wires can take advantage of services, advanced services offered by SD-WAN. what will happen is that the cloud native WAN adaptation layer will talk to the network service registry, get the necessary metadata for each of the network service endpoints so that the SD-WAN can optimize traffic for each of the virtual wires specifically for their needs. So the DevOps, basically in the previous slides from the presentation, are going to be writing the Telepharma application and deploy it on this and in the headquarters, and they will be able to tag each of the microservices that are the components of this application with the necessary information, both for the network service endpoint point of view and also for the CN-WAN point of view, so that CN-WAN can optimize for the specific needs of these microservices. For example, you could have from the kiosk a video feed to the headquarters. A different microservice could access a secure database with highly confidential health data for patients. The other one with prescriptions, drug information, and so on, which may need to connect to different backend databases. So this is where the CN-WAN comes in to optimize traffic through the virtual wires and give them the traffic characteristics that they require. So Alberto, maybe do you want to summarize?
Yeah, sure. Thanks, sorry, for the example. Yeah, just a quick recap of what we explained. So yeah, NSM creates some vWires and SD-WAN carries those vWires, right? So you can have the vWires whenever there's SD-WAN. So with CN-WAN that in general optimizes SD-WAN for cognitive overload, you can also optimize those vWires going over the SD-WAN. So yeah, if we go to the last slide, yeah, this is the last one we have. Yeah, maybe before I mention this, let me say that what we saw in the slides regarding NSM is just slideware at this point, so we have no code for NSM yet. We do have code for the cloud native SD-WAN in general, and that's available on the repo that you see there. We need to iron out the details with the integration with NSM, because drawing arrows is easy, but the details is where you can get lost. But if you guys have either ideas on how the integration would make more sense, or if there is a use case that could interest you because you have already use cases that match with what we are looking at here, yeah, please reach out to us and we can talk and discuss. So here is the GitHub with all the code and some info. So the documentation is really short at this point from what it should be. So if you try to deploy something and you succeed, I would be really surprised. But we will do our best to improve the documentation over time. So the code is working and the documentation will be there over time. If you want to play with this, just send us an email if you don't find your way around. Also, there is a demo about CN-WAN on the Cisco virtual booth that I guess that is available today already. So if you wanted to check the video and we show the Kubernetes annotation that we use and so on, that you can watch the demo there. Yeah, and I think that's it. Happy to answer any questions now on Slack or send us an email and we will be happy to chat with you guys.
Thank you very much. We'll give a few moments to see if any other questions come in. Okay, I am not seeing any additional questions. So thank you for presenting the cloud native SD-WAN. So we are going to take a break. We will be back at at the half-hour mark. We're going to take 30 minutes worth. And Ed, do you have a slide that we can stick up that has the return?
Yeah, give me just 1 second. Hang on.
No worries. So after that, we have two more conversations at 10:30. Sorry, 10:30 Pacific. That's we will have simpler, faster, more flexible forward evolution of NSM, and given by our very own Ed. And then we will have NSM customer success, QoE, L3 VPN, and NAT64. Oh my. And that will be given by Zia and Bruce with content that was initially put together by them in conjunction with Daniel Bernier. And he was unable to make it because he's on vacation at the moment. But beyond that, we will see you in about half an hour. Hello, Ed.
Hello, hello.
So we'll give it another minute, then we'll get it kicked off.
Sounds great.
Okay, let's get started. We have Ed Warnicki, Distinguished Consulting Engineer from Cisco and co-founder of Network Service Mesh, here to talk about simpler, faster, more flexible forwarding evolution of NSM. You have the floor.
Excellent. Thank you so much. So, as is often the case, when you're going to talk about the future, you often find yourself talking a little bit nostalgically about the past. So you have to sort of look back to where Network Service Mesh came from. And it started with a very basic dream. And the dream was to be able to solve the unsolved L2, L3 problems in Kubernetes in a cloud-native way. Now, and part of what made this challenging was Kubernetes networking is actually incredibly well done for a very large set of the use cases that people might want to do. So for most of the users of Kubernetes networking, there actually wasn't a problem. And the vast majority of the solutions that were being proposed to try and extend it to be able to solve broader sets of problems actually were a problem. They involved importing very antiquated models of how you do networking from Cloud 1.0 into Kubernetes. And that ended up not being a viable path. And so Network Service Mesh was sort of born from a very basic plan. Borrow the ideas from application service meshes, things like Istio, Linkerd, et cetera, and apply them to the L2, L3 payloads that we were familiar with from broader networking. And so you start with the most basic notion, which is any service mesh you have has a service registry, in our case, a network service registry, where you keep a list of your services and the endpoints that provide those services and various metadata associated with those. And so the very first people we hit when we went to try and do this is, unlike when you're trying to write an application service mesh on top of a HTTP web proxy, there's no one true connection protocol like TCP for things that carry L2 and L3 payloads. So we created one. We created a gRPC API to, in a very generic sense, let us say, look, we'd like a virtual wire that connects us to a network service, and we'd like to be able to ask for it and get it. We'd like to be able to close it, and we'd like to be able to tell what we actually have going on. And this actually worked remarkably well. So we spun up the network service mesh repo, people started contributing, forward progress was being made. Stuff started working. So we had a lot of CI up and going, doing continuous integration. That CI was running on GKE, EKS, AKS, vanilla Kubernetes. Everything was working pretty well. And then we realized that this is actually bigger than a single cluster problem, right? The real power of it actually comes in being able to conceptualize network services as things that are not attached to your particular cluster. You know, floating network service domains that different workloads at the granularity of workloads can connect to. And in fact, we went on further to realize this is bigger than just Kubernetes either, because the same tricks that we use with network service mesh for allowing individual workloads to get precisely the network services they need, independent of where they're running, also extend equally well to VMs and on-prem services, on-prem servers. But then complexity grew. As you actually try and do things in Kubernetes, you discover that you need more components than just endpoints that provide services and clients that consume them. We needed things like the network service manager to allow us to have a single point of conversation there. We needed things like Forwarder to handle like very pedestrian things like cross connects, where one side wants a kernel interface, the other side wants an MIF or a VXLAN. And so the components started proliferating, which is not necessarily so bad. But the worst problem was that the API started proliferating, right? So what it started as a very simple API to stick things in the registry and to ask for network services, picked up things that were similar in form, but to go and program cross connects into forwarders. And this worked, but it introduced a lot more complexity into the system. You know, you can sort of see here the diagram of how this went. You know, the network service client would ask for something, the network service manager would find the network service endpoint and request the network service from it, get back the parameters, and then we'd have an entirely different API that programmed the forwarder, and we didn't actually know anything other than what we've been told in the forwarder registered when we did this, and we didn't have any terribly good way to bring in multiple forwarders, and there was definitely a lot of interest in having multiple forwarders, because as it turns out, there are a lot of approaches to that part of the problem, and they all have different pros and cons to them. And so you want to be able to support them, not just as choose one of these, but as a take whatever set of them, actually solve your problem. And that was the first point at which we realized that a little bit of simplification was going to be needed. And that was not supposed to go there. Why? Oh, hang on. Let me, are you guys seeing this presented or?
Yes, we saw the
I'm back.
yes.
Yep, cool. And then the last thing that happened was, you know, so we got the API proliferation. From there, we started noticing other things, like the CI had slowed down, right? So it was now taking an hour and 40 minutes or so to do a CI run every time you pushed a patch, and this is wholly unacceptable. It also started getting hard to add new features to the system because there were so many pieces that were just slightly different in their API to deal with, and so many components in the system. We proliferated a bunch of internal APIs. Turns out internal APIs make things very hard to evolve, etc. And so we went and took a look at doing a simplification. And it turns out simplicity is a almost unalloyed good. Simple systems tend to be robust, they tend to be resilient, they tend to be secure. And so you want to try and keep your entire system as simple as you possibly can, but no simpler. And so looking around, we realized that fundamentally there are only really three kinds of things in the network service mesh world. No matter how many different kinds of components we had, everything was either a network service registry, someplace where you scribe down the network services and their endpoints, or it was a network service client, something which wanted a virtual wire to a network service, or it was a network service endpoint, something which was involved in providing a network service to a client. And so from that, we could clearly see that the fewer APIs was going to be better, right? So network service endpoint was going to need to register and unregister with the network service registry. The network service client was going to need to potentially find, or something on its behalf was going to have to find, network services from the network service registry. And then our old familiar request, close, and monitor were still there, but it was all request, close, and monitor a connection for a network service. And this also made it easy to secure, because if you construct it this way, you can basically bring in SPIFFE, SPIRE, and OPA to secure these conversations, because they're very primitive conversations, and they're potentially pairwise conversations. So your network service client and endpoint could both have cryptographically authenticatable identities, and you could use Open Policy Agent in your network service endpoint in order to actually restrict which clients were allowed to talk to that endpoint. You would likewise use that to restrict which clients were allowed to look things up on the registry if you needed to, and what's allowed to register or unregister for a particular service. And this also ended up making it easy to heal. In the first turn of the crank with network service mesh, we had a fairly robust healing process. You could kill any one component in the system. You could kill off the network service manager on a node and it would restart, and then everything would be fine, or you get good recovery of the system state. Same with the forwarder, or the remote network service manager, or the network service endpoint. You would lose any one component in the system, and its neighbors could reconstruct the state that you had lost, and you could restore exactly what you were looking for. But as the number of components proliferated and the number of APIs proliferated, this got to be quite complicated. And we were still at a place where we could only lose one piece of the system at a time. And so in looking at resilience and healing, it turns out that the best way we could find to approach this was to say, from the client to the endpoint, the client should monitor to detect if the endpoint doesn't believe it has a connection for that client, and if it doesn't, re-request. The endpoint should expect to receive a refresh from the client before some expiration time for that connection. And if it doesn't, it cleans up resources by closing connections. And likewise, when you're talking about registering endpoints, you should expect registration to use the endpoint to use find to detect when the registration is missing and re-register itself. And likewise, the registry should, after some expiration time, if it doesn't receive a refresh of its registration from the endpoint, should simply remove that entry from the registry. When you set the system up this way, it's a fairly clean and simple set of fast healing together with acceptable levels of cleanup of resources over time. And essentially, this basic pattern becomes whatever client in the system you have, it detects failure fast and it repeats the request. If all the requests have expirations, and the client repeats the request before it expires. So it becomes literally impossible for the server to tell the difference between a refresh of a request and a heal request. And then the server just needs to eventually clean up any expired state that it's accumulated, whether that's a connection for a vWire or a registration in the network service registry. But this is all well and good when you're talking about pairs of things. But number one, people really like the fact that you can compose network service endpoints together to form a network service. And number two, it turns out the world is actually more complicated than simple pairwise behaviors. So for example, you probably, if you're a normal pod on a Kubernetes node, need a little bit of help getting off the node, because there are things that are required to get off the node as part of network service mesh that require privilege, and we don't want every single workload to be privileged. And the approach to this then is you get to complexity by composition of the same pattern again and again and again. So your client asks an endpoint, which may itself be a client, which asks an endpoint, which may itself be a client, all the way down the line. And a network service endpoint may or may not, as part of the work that it's doing to help you get what you want, have a data plane associated with it. So for example, if you look at the Kubernetes case, you've got a network service client sidecar in your workload pod. the network service manager primarily is actually not shepherding a data plane. It's doing very basic work around trying to resolve what network service endpoints you might be dealing with, what forwarders you might be going through, et cetera. This is very similar to the observation earlier today in a previous talk where they were pointing out that you actually could have network service endpoints that did not actually have data plane pieces themselves. Now, this does introduce one wrinkle to healing, because you would like to be able to heal in such a way that if you lose some element in the system, say if your network service manager restarts, you would like to be able to get back as close to what you had before as possible. And the way that we accomplish this going forward is with paths. And a path is very simply a repeated set of path segments and the index for where we are. So every time you get a request going along the hops between these NSEs, it has a notion of where it is in the path, and you have, for each path segment, the name of the entity, the network service endpoint that was in the path, or client, whatever ID it uses locally, a token that can be used so that it can authenticate when something is presented to it for refresh, whether it should permit things to go forward, and a timestamp that gives you expiration. Additionally, we realized that it's very helpful to have the metrics associated with each hop on the path, so that, for example, if I have a network service client running in a cluster that ends up going through many hands on the way to a network service that's running, say, in another cluster, another zone, another public cloud, that I can actually get metrics that tell me exactly where along that path things have broken down. Makes the entire system substantially more debuggable. The next thing that became very clear was we needed to improve our modularity. So we already had an SDK, and as far as it went it did fairly well. You actually have seen people use some of the internal tracing bits that it has in their applications for Jaeger, just to sort of see where things happen. But we wanted to take it sort of to the next level. And essentially what we ended up doing was building out chain elements that did all the pedestrian bits that you don't necessarily want to do when you're writing your network service endpoint. So it's probably not the case that you want to handle the basics of path updates, token updates, timeouts inside the server that you're writing. You have a bunch of stuff that here we've labeled as additional functionality that you basically would like to have those be the pieces you work on. And so, for example, we have an endpoint.new service you can call, providing a small number of parameters and the list of your chain elements to do the bits of work, the programming firewalls, programming your data plane for your NSE, or whatever other interesting bits you're doing, rather than having to rewrite all the logic for everything going forward. And as we sort of expanded out, we've written a bunch of granular pieces of this. So something that plugs you in as a kernel thing or a MIF thing, for example, to VPP agent or to some other data plane. And you've got a similar sort of behavior with clients where, again, the first step anyone needs to do is to authorize. All the healing and refresh behavior is encapsulated, the update token pieces, et cetera. And it turns out this actually turns into a very powerful pattern because it means the various concerns in the system are highly localized. And because the only thing you end up doing from one is calling the next instance of the API, and it's the same API as you received, the amount of trouble you can get into with unduly binding together the pieces that you constructed as chain elements is relatively limited and well-defined. And so it becomes very possible, and the system strongly influences you towards writing very self-contained chain elements that can be composed together in chains in order to achieve a wide variety of ends. So, in fact, I will often point out, if you look at it this way, network service mesh is actually fractal in nature as a system. Down inside an individual client or network service endpoint, you have little tiny chain elements that are calling each other through a chain. Then from there, you might have your client calling a network service endpoint that does some of the work, say some of the work to get you off the node in terms of resolution and lookups. which then calls the next component, say a forwarder on the same node, to get you out of that. As you saw in the talk earlier about interdomain, as you reach the edge of your cluster or your cloud provider, you may hit another network service endpoint in there as a proxy network service manager, is what they were generally called, that literally all it does is accept the call along the chain and do the next little bit of work in order to solve the problem. We also realized that part of the reason our CI was slowing down was we were trying to do absolutely everything in a single monorepo. It turns out that monorepos have a small number of advantages, particularly when you're first starting. But as you go on and on, they do have exactly the kinds of situations that we were running into. You tend to wind up with stronger coupling than you intended between components. Your CI begins to slow down. You suddenly discover that you have multiple Go modules in the same repo, or that you're actually building 7 or 8 or 9 or 10 different Docker containers in the same repo. And so we started exploring a multi-repo approach. And so the first simplest one we did was just the Network Service Mesh API repo. It's a place to put all the APIs. It's basically some protobuf definitions and little bits of top-level NSM API. But the problem, of course, when you go to something like multi-repo is, how do you keep the pieces in sync? And so the very first problem we ended up solving was, how do we auto-propagate down the chain of dependencies of the repo? So for example, the SDK depends in a Go module sense on the API. So every time a change comes into the API, it will automatically push a PR to the SDK that will update the dependency version to point to the new version of the API. If that passes CI, it will be auto-merged into the SDK. If that auto-merge succeeds, you will then get PRs pushed down to various platform-dependent SDKs, things like SDK VPP agent or SDK kernel, etc., and possibly down directly to individual commands. And these individual commands are the components we know and love. They're things like command K8 network service manager or command K8 forwarder dash something. And these different command repos are those sort of individual components. But again, all of them are either service registries or NSCs at the end of the day that do some small part of the work involved in getting you what you really asked for from network service mesh. And then finally, once your commands have been built, you propagate down to various deployment mechanisms like Helm or operators, and down into integration platforms for the various places that you run and test. Things like Kubernetes on Packet, Kubernetes GKE, EKS, AKS, et cetera. And one of the nice things about this is, if you decide that there's a new environment you want to integrate against as part of your CI, say OpenShift, you simply can add another repo. The people interested in that can work on it. Things can be auto-propagated to them, and you keep moving forward. So this gives you some idea of how this impacted our CI time. So the API CI takes about 1 minute and 20 seconds to run. SDK is a little longer. It takes about 4 minutes. The platform-dependent ones take about 3.5, and so on down the line. So if you're really talking about the end-to-end propagation of a change, presuming that nothing goes wrong, it's about 15 minutes end-to-end. But if you're just trying to make a change because you wanted to fix a comment in the API to improve it, or because you're introducing a new chain element into SDK VPP agent, you're looking at very short timeframes to get CI feedback on your patch and be able to merge it. Which of course begs the failure detection and mitigation question, which is, what do you do when things go wrong? So you start with something, say an SDK for VPP agent, and it propagates down to the various command repos, and they propagate down to the Helm and operators, and that propagates down to an integration test that fails. You can actually chase the failure back to the offending patch. Depending on the seriousness of the issue, you can go fix it upstream, or you could revert it upstream until you sort out exactly what you're going to do about it. And having put the fix in, you can add unit tests to the platform level to make sure that you don't get that particular flavor of escape again down to integration. So, questions. Well, first, special thanks to our event sponsors, Anthem and Cisco, but would love to take questions. I'm going to leave presentation mode because that lets me actually see the questions.
I put a question in the NSM Slack.
Let me go take a look.
Yeah.
So is there anything to prevent you from doing update path before authorize in the NSC example? All right, so let's go back and take a look at that particular example. And you're talking about the client.
Yeah.
So I tend to think about the world in terms, let me put it this way. Engineers are lazy. It's what we pay them for.
Yeah.
And if I give you a handy function called new client that you only have to fill in the blanks for, now you're going to generally find that almost every engineer will use it unless there's a really good reason they think they need to do something different.
I agree, but
So,
this is a set, but it should be a sequence, as I see.
I'm sorry, I didn't quite hear you.
This is an array. I mean, when you do append, you will have an array. So the functions will come in a sequence, and they are actually decided. I mean, there are some combinations here that are completely useless, so you shouldn't be able to do them. This is what I mean.
Yeah, so effectively, I have sort of a mathematician's attitude towards that, which is you can do, let me sort of put it this way. We're all engineers here. We all know that occasionally you have to do something that you really think is a bad idea in order to make something work or to deal with a problem that you did not foresee. So rather than putting very hard limits in that make it impossible, for example, to switch the order of authorize or update path, which I would not recommend, by the way. But rather than hard coding you in where you have no choices in that matter, we make it instead so that the easy path is to do them in the correct order. I mean, please note, for example, you would literally replace update path if there was some particularly good reason you needed to as a chain element. All the chain elements could in principle be replaced one by one as needed. However, it's going to make your life much harder. And going back to the engineers are lazy, it's what we pay them for. That's the fundamental social limitation on engineers doing particularly stupid things.
Yeah, I still think it should be possible to do stupid things. So it's not that. I think that the default should be more like pushed, because I remember sometimes very early in the NSM history, you reversed this list like a year ago or something. And we had a lot of problems with that. I mean, yeah.
Oh, okay. So I see sort of your point. I mean, part of what it comes down to is that since you have client calls, essentially one client calls the next in the chain, and then the returns go back the other direction. So part of the question becomes, are you doing work on the way in, or are you doing work based on the return?
Yeah, and can you guarantee you will do it in 2 years in the same way?
So for example, if you are writing a piece of a client that is going to plug something into a vSwitch like VPP, to plug it into the vSwitch and VPP is probably going to end up being done as part of the return part of that pass, not on the way out, because on the way out you don't actually know what your connections look like. So let's see, we had someone who raised their hand. Let me see if I can find that information. So yes, so there's a question online where Shini was asking, does this change include support for multiple data planes? It was literally motivated by the desire to support multiple data planes. That's kind of where we started.
Yeah, I know.
Not just multiple data planes, but multiple simultaneous data planes.
But you have the same construct today, even in the old. I mean, if you went into a network service, you have the same. You do the composition of the IPAMs and stuff like this, you know. Yeah. But maybe it's not important. I just wanted to know because what you say that the designer should be lazy and steal the code that exists and don't think too much about it.
Yeah, I mean, don't think too much unless you have a hard problem to solve. I'm very much in favor of thinking when you have a hard problem to solve. So someone raised their hand. I'm trying to figure out how that worked and who. So excellent. So, and please note, this is stuff that's been going on in the background in the community at this time. We've been building this out for a little while. Some of you have probably seen some of the pieces go by. And these pieces, as they've gone by, have been sort of very openly discussed in the community as we've gone. That said, I think we care a great deal about usability of the system. So for example, you'll find that other than the introduction of paths, which adding new fields in gRPC is relatively straightforward, you haven't seen a whole bunch of shift in terms of the semantic content of the APIs, for example. So Charles Eckel has raised his hand. Let me see if I can figure out how to unmute him. Okay, you appear to be permitted to talk, Charles. Did you want to say something?
Hello, Ed. No, actually I didn't. I don't know what I did to raise my hand, but it was an accident. So great talk though, appreciate it.
Cool. So we are right up against the time. I would be delighted to discuss this with folks in the NSM Slack channel, and basically in pretty much any other conversational venue. It's one of the things I'm very passionate about.
Fantastic. Well, in that scenario, let's go ahead and move on to our last conversation. NSM customer success, QO3, L3 VPN, and NAT64. Oh my. So I'd like to welcome, and I apologize if I get the name wrong, Zia and Bruce.
Hey, Frederick, thanks. I'm trying to enable my video and it says that the host has stopped it. So
hang on, we should be able to fix that. Give me 1 second.
Okay.
Yeah, a little bit of a weird thing with this. It requires us to make you a co-host and not just a panelist, despite the fact we asked it to. We just asked it not to start the video when you joined, and it seems that it's conflated the two of them.
Yeah, let me see if I can find Zia. Is Zia on the call?
No, Zia also had a scheduling conflict. So okay. Yeah, I'm substitute presenter for all.
Okay, excellent.
All right, looks like video is up. Cool. All right.
Yeah, try to share and make sure that works.
Is that coming up?
Yes, it is.
All right, great. Okay. Well, thanks all for sticking around and staying on. I think this is the last presentation. So, and this is NSM Customer Success, QoE, L3 VPN, and NAT64 OMI. My name is Bruce McDougall. I'm a principal architect at Cisco. This effort was a collaboration with Dan Bernier from Bell Canada, and then Zia Syed as the original developer for the proof of concept of the Jalapeno project that underpins some of the work here. So I'm going to quickly go through an agenda. In 2019, at the NSMCon in November in San Diego, essentially a collaboration was born. Then go through Bell Canada's goal to transform themselves and their services to cloud native, and then an SDN problem statement. The network black box is kind of the barrier to a lot of SDN use cases, we feel. And then I'll do an overview of Project Jalapeno, which is our generalized SDN proof of concept platform. And then the collaboration with Bell, how it's basically how we're putting together NSM and Jalapeno to build a cloud native layer 3 VPN NSE. And then there's also kind of some roadmap NSEs that, that the title alludes to with the quality of experience in NAT 6.4. And finally, a summary. So, like I said, collaboration was born at NSMCon 2019. At NSMCon in San Diego, Dan Bernier from Bell Canada presented essentially an architecture, a desired architecture designed to build out a cloud native service provider or telco services. And he felt at the time that leveraging SRv6 as the underlying data plane would be a very valuable method to approach this. And what he wanted to do is convert essentially NFV kinds of functions or VNFs to cloud native. And a key problem statement that he articulated at the time is the need for tight coupling between cloud and metal. Earlier in the day, oops, sorry, forgot this was a build. Earlier in the day, Zia and I had presented on our proof of concept project, Jalapeno, which at the time we were kind of thinking of it as an SDN sort of proof of concept project that could execute like quality of experience use cases for cloud native applications. So you could do traffic engineering essentially. And the two together, after Dan presented and after we all got talking, we realized that these two projects are completely complementary. So we essentially made arrangements for a trip to Montreal like 2 weeks later and had a day of wakeboarding, and things got launched from there. So Bell Canada's ultimate goal is to move to, like I said, cloud native telco services. And there's some key requirements there to execute on that goal. First of all, the application workloads themselves need to be able to request, say, network service contracts, things like security or an SLA or a VPN. And then we need to be able to abstract the complexity of the network away from the user or the application, the workload itself. And then the third requirement is that the network should dynamically adapt to changing conditions within the network itself. And then Dan also articulated, or Bell has also articulated, that this sort of move toward application responsive networking they felt is very achievable via implementing a unified forwarding plane, segment routing end to end, essentially. But then, like the earlier slide mentioned, there is that gap. It requires bringing SR to the application workload itself. And so what they've articulated as the software edge. And really, if for non-network engineers in the audience, in the service provider world, the network edge is kind of, it is the end of the service provider network, BGP environment. And anything beyond that is, say, is customer, so to speak, or potentially application. So that software edge means that the service provider network actually needs to be extended into the server host itself, which leads very nicely into the SDN problem statement itself. This is from Zia's and my presentation previously at NSMCon, where we articulated, with Project Jalapeno, we articulated the exact same problem space that Bell Canada had. Looking at SDN use cases, you've got applications and people or stuff that applications would like to communicate with. And in the middle, you've got this giant network black box. And so from the application's perspective, this is how the world works. And maybe you've got some SDN controller up there. So the application makes a request to the SDN controller. The SDN controller is a network-centric SDN controller, so it executes some magic within the network black box, and the application is left to wonder if it worked or not. So that's the gap that Bell Canada and our team are looking to close. And so Project Jalapeno is specifically designed to do that closing of that gap. So Jalapeno is a proof of concept project that Zia and I and a couple other folks have been kind of working on for about 2 years now. And we articulate some very specific principles guiding the project. First of all, that SDN is not about controllers and protocols. It's actually really about databases and APIs. And number two, we want to give applications the ability to directly choose their service. And this maps perfectly with what Bell Canada wants to do, where they want to also essentially do exactly that. And we want to, from the ground, from the get-go, we wanted to expose those service attributes via an API as opposed to, say, some, make it available via like a PCE protocol or something like that. Ultimately, those three, we look to eliminate the network black box. We want to perform the SDN encapsulations at the server itself. Jalapeno has also been designed from day one to be microservice-based. It's Kubernetes-based from the outset. And for best results, we want to ideally combine network and application performance data. I'm going to kind of whip through these slides for the sake of time, but Jalapeno is architected sort of in three main pieces. There's a data collection stack where we're collecting network topology and network performance data. And we aggregate that data all through Kafka, which is pretty natural. Then we've got a series of data processors that we've built where they're taking the data off of Kafka and mapping that data, both the topology and the performance data, into a series of virtual topologies in a graph database. And Tim and John in their talk earlier mentioned, or I think there was some discussion of graph databases, and this is very, very powerful and useful, where essentially we've taken the network topology itself and we can map it into n number of possible virtual topologies. So there's the underlay topology itself, like say if you're running ISIS or OSPF, but every VPN is also a topology, a virtual topology in this data set. And so with Jalapeno, the goal is then to expose those virtual topology data sets via an API gateway. And from there, a little bit more build, an application or end user or host or whatever could be seeking to request network services, make that request via the API gateway, and the API in turn, after some mining of the database, can respond back with a label stack or say an SRv6 SID value that can then execute the use case that the application requested. So with that bit of background, with Jalapeno essentially looking to close the network black box gap, or that service edge gap where we extend the network into the host, we can now combine Jalapeno with NSM and try to create network services that do exactly what Bell Canada wanted to do. So here I've got a diagram of essentially an example network. I've got customer sort of on the left, connected via a service provider router. There's a metro network, say a central office data center, and a wide area network. And in our first use case, Bell Canada wants to be able to connect a workload that's say in this server here to the VRF instances that this customer is participating in. So this could be, say, you want to connect like something like a firewall VNF or something like that. So the first thing we do is we've actually built a layer 3 VPN NSE. And that layer 3 VPN NSE has, as in Tim and John's presentation, as well as in Ed's discussion, it's got a decoupling of control plane aspect and data plane aspect. So the layer 3 VPN NSE has a VPP that it comes with. Now our containerized VNF in NSM context, it spins up, and as it spins up, it's going to request to join VRFs red, green, and yellow. So it might just request to join a single VRF, but in this case, we actually built it out to be able to join multiple, as Bell has use cases for that kind of thing. And in our case, the NSE may be co-located on the same server host as the client for performance reasons, although it's not a requirement. Here's some sample YAML for the client's request, and just to highlight down here, the layer 3 VPN NSE request for VRFs to join. So as the system works, the signaling and VRF programming, after the client makes its request, NSM is then going to signal to our layer 3 VPN NSE, which has pre-registered to attach the client to its VRF instances. So the NSE will then essentially, it'll plumb those interfaces to the NSM forwarder data plane or cross connect that got established. Next, our layer 3 VPN NSE, it doesn't have the layer 3 VPN BGP table itself. It's not actually a BGP speaker. What it does is it queries Jalapeno, which has the VRF fib tables already. So it asks for, give me essentially all of the destination prefixes in VRFs red, green, and yellow. Jalapeno responds back with that data set and corresponding, in this case, SRv6 SID values to execute the VPN encapsulation. And then the layer 3 VPN NSE programs VPP with SRv6 VRF instances and SID values for performing the encapsulation. So at this point, we've actually established that now the client has essentially a routing table for all 3 VRFs and can send outbound traffic to, say, the customer end in VRF red, and also to, say, endpoints on the green and yellow side. But now we need to establish a connection back, or the ability for those endpoints to communicate back with the client. So the next step is the layer 3 VPN NSE. It'll signal to a GoBGP instance that's running in our cluster to issue a layer 3 VPN advertisement of the client's subnet on behalf of, essentially on behalf of itself to the remote PEs. So that BGP advertisement then flows through the network via route reflectors and things like that, and remote PEs get it and program their forwarding. And now we've got end-to-end bidirectional communication established. So the client has joined the layer 3 VPN instance. And I wish I had a demo to show you all, but because of scheduling and such, we're not ready for that. Hopefully we'll try to post something though at some point. So that's currently in proof of concept and in our lab and in Bell Canada's lab, and we're actually targeting a initial sort of a canary production deployment by the end of the year in Bell Canada's network for the layer 3 VPN NSE and this service. And then on our to-do list, the stuff we have coming up next is we want to be able to add like a quality of experience traffic steering to that layer 3 VPN service. So let's say for a certain given set of prefixes, if it's high priority traffic, we want it to take the best path, or the lowest latency path, or whatever path has the attributes that achieve that high priority SLA. And let's say for low priority traffic, let's say for backup traffic or something like that, we can actually steer that traffic off of the best path to a lesser utilized and less important path. So those are goals for the quality of experience traffic engineering. And then also Bell Canada has a use case for a NAT64 NSE that can simply do translations from 4 to 6 and vice versa. We also have brainstormed any number of other use cases or NSEs that could make use of the combination of NSM and Jalapeno's virtual topology data sets. So more to come. So in summary, Bell Canada's application responsive networking goal, again, I'll kind of sort of restate their requirements 1, 2, and 3. The first requirement being that the app can request some network service contract. And then the network also, the constructs must be abstracted away from the application workload. So in this case, NSM provides that abstraction and menu of services. And then Jalapeno provides the virtual topology mappings that can execute those network services. And NSEs can leverage or program encapsulations or forwarding via the data set that Jalapeno replies with to any request. And then the layer 3 VPN NSE itself completes the connectivity between the client and those VRF instances. And again, to highlight, we're doing this with SRv6. The third requirement, that the network should dynamically adapt to application-specific patterns. So within the layer 3 VPN NSE, if prefixes are deleted or withdrawn or added to the VRF instance itself, the Jalapeno system, its database updates, and the layer 3 VPN NSE also updates. So from a straight layer 3 VPN aspect, the network and the NSE do dynamically adapt to those kinds of changes. As far as, say, performance changes or SLA changes within the network, like I said, that is kind of phase 2 of the journey, where we look to do quality of experience engineering. And then number 4 and 5, this is achievable. We've demonstrated that this is very much achievable with segment routing. We've done proof of concept with both segment routing with MPLS labels, if you will, at the VPP, as well as segment routing SRv6 with SRv6 SID encapsulations. And then the Bell problem statement that it requires bringing SR closer to the application workloads, which matched the Jalapeno problem statement that the network is a black box. By moving that network functionality, that encapsulation functionality directly into the server host, we now have the ability with network service mesh to attach those workloads directly to their VRF instances, or potentially like an SLA forwarder and that sort of thing. So confirmed there. And with that said, I kind of blasted through this, but wanted to give quick acknowledgements to the team. So obviously Mr. Bernier from Bell Canada, Zia, who's the initial developer on the Jalapeno proof of concept. Sergey Bezverke is a Cisco developer in Montreal who built our layer 3 VPN NSE. Terry Couture is the lead architect for Cisco on the Bell Canada account. And then Ed, our NSM Oracle. And the entire Cisco SRv6 engineering team has been executing, and they contributed code to VPP for SRv6 encapsulation as well. So with that said, thank you for our sponsors, and that is my talk. Do we have any questions?
So there are some questions in the chat.
Okay.
So basically, Roshini asked, are these NSEs planned for upstream to the NSM project?
The NSEs, I don't know yet. They're considered at this time, I would consider them Bell Canada's intellectual property. I mean, they're paying essentially a service contract for Sergey to build them. Jalapeno itself, we plan to upstream here pretty soon. Not to the NSM project itself. It'll just be a separate organization and set of repositories. But yeah, the NSE side is a TBD.
Well, it looks like that answered Rashid's question. And then we had a similar question from Michael Hernandez on the Slack NSM channel. L3VPN NSE code has public access ? Documentation / code POC is available ?
I would love to make it available. So I'll talk with Dan about that when he gets back and see what he wants to do. Because that would be pretty cool.
Yeah, I would love to see something like that in the repo as well. In short, if you don't open source it, it's very likely that there will be other groups that'll rebuild the same type of behavior and open source it as well. And so open sourcing that, I don't think that specific component, I don't think is your core source of value, but rather the additional services you provide around it and your reputation as a company. So I would love to see something like this hit the repo if you're able to make it happen.
Yeah, cool.
And just to be clear, I don't think anyone's terribly religious about what repo things land in. But if it does land in an open source repo, I think we need to start actually getting serious about collecting pointers to things, because we're starting to get enough people doing enough interesting things in various repos that are not part of the network service mesh org. And that's actually a really healthy sign. So it's more power to everybody who's doing that. But being able to find them is sort of an important thing for the community.
Yeah, great point there.
Yeah, this was, I'm sorry, please continue.
I was going to say for Jalapeno, when we do open source it, we'll definitely include pointers to NSM because it's been a terrific collaboration between two projects that are highly complementary. But you were going to say, Frederick?
I was going to say this was a fantastic talk, by the way. Like, I'm really glad to see how things have progressed since was it November of last year? So fantastic progress from you and your team.
Thank you. Yeah, been really excited. The team has done great work.
Looks like we might have another. Somebody's typing something in Slack.
Okay.
Another question would be fantastic.
I haven't connected to Slack. Apologies.
The typing disappeared. Anyways.
Okay.
Cool. Well, thank you very much for the presentation. So that there was a question: is Jalapeno open source? They mentioned they plan on trying to open source it. Is that correct?
Yeah, goal is end of August. We're talking with some folks in legal here later this week, actually, about some specifics that we need to do to get that done.
Fantastic. And there's one more person. I can see that they are typing on Slack. So let's give it a brief moment more. Just a thank you. Yeah, and thank you for attending a bit, and everyone else as well. Cool. Yeah. So that concludes our line of talks. Do you have the energy to open it up for a few last set of questions in general?
Absolutely. I always love questions.
Cool. Well, if anyone has any questions, we still have several panelists on the call who have helped, and Ed and I are willing to answer questions as well. Well, I'm not seeing anything at this particular point. All right, well, in that scenario, just as a reminder, you can visit us at networkservicemesh.io. And all of these talks and their presentations, Ed and I have been uploading all the slides that we have to the events page in the networkservicemesh.io website. If you are a presenter and you haven't sent it to us and you wish to have your presentation in the website, please let us know. We'll put it up there. And we also intend to make it easier to get to some of these videos in time. So the video was live streamed on YouTube, and so you should be able to visit that same link and see the recording in its entirety. And hopefully in the near future, we'll be able to break these out into their individual talks to make it easier for people to discover and listen to. And
so you can sort of see, I've got on the share right now, sort of where the slides have landed. Being firm believers in localization, the place you went to go get all the information about the talk on the website is exactly where the slides land, and that's exactly where the individual video links will land as soon as we get a chance to edit that into the appropriate pieces.
We also have included GitHub and LinkedIn and Twitter information when available in case you want to reach out to people. And of course, you can always reach out on Slack. The NSM channel that we directed everyone to for this talk is very active. And if you ask a question, we have people around the world who are working on NSM. There's very likely you'll get an answer in relatively good time if you hop in and join us and ask questions. And so we also have our weekly meetings every Tuesday at 8 a.m. Pacific, except for this week. This week we decided to pass because of NSMCon. But next week we'll be back on our normal agenda, and we hope to see all of you there. And with that, I want to thank everyone for your time, and you all have a fantastic rest of your day.
Cool.